Let's check the audio. 1 second. I think the audio should be good. Let's share. What should we share? Nothing for now. What I would like to look into is dark matter. I want to understand exactly what is dark matter, so let's close. I'm listening to the audio. I guess it's okay. Let me see over there. 1, 2, 3. Guess it's okay. Yeah, sounds good. Okay, so what we're looking into is dark matter. Is that what I wrote? Yeah, dark matter. Okay, let's close some windows. So dark matter. The question is, what exactly is, what is the evidence for the dark matter question? Why do we even have a dark matter question? Okay, so let's share this. Let's look into dark matter. What's this? The secrets of the universe. Baker, Islam in the West, quartering, maybe just before anything, I just wanted to express my current understanding of quantum mechanics. It's becoming this is dangerous, because you can see this. So you can see private stuff. If there's any private stuff in any of my window titles, this would show up. Dangerous. Anyway, so let's go to whiteboard. I just want to show you my current understanding of not dark matter. No, not dark matter. My current understanding of quantum mechanics. So I don't think there is a wave collapse. So one of the major problems that I was having with quantum mechanics is this wave collapse and entanglement. So I no longer have this issue. This was basically the biggest issue. So I removed that. I no longer have that issue. I need to look into Bell's theorem. Maybe there's an issue with Bell's theorem, but I don't have a problem with entanglement anymore. There is no entanglement, which is actually pretty incredible. So the way I see quantum mechanics now, let's look at the double slit experiment and see that there's no issue, right? Because last time I described the double slit experiment, I would have had to use superposition or entanglement or some other magic solution that made no sense, some violation of the speed of light, some instantaneous intelligent communication, some roll of the dice. All of that went away. I no longer have that issue. And so at this point, for me, quantum mechanics is almost completely mechanical, almost completely resolved. Almost. I still have questions, but I think I have less questions than answers. It's mostly straightforward and mechanical. All right, so let's talk about the double slit experiment. So here is a gun. It's an electron gun. It fires electrons. We'll discuss electrons in a second. And here is a barrier with two slits. So it can't look like this. It needs to look like this. And like this. And like this. So it's the two slits. And here is the screen detector. Okay. So when we fire an electron, it's no longer a complete wave. I used to think of any particle as a complete three-dimensional sphere. I used to say this all the time. Every wave is a three-dimensional sphere. And because of that, it used to expand over the universe to both sides of the universe and into a black hole and outside of a black hole. It used to go everywhere. And then it used to have to decide to collapse into one place. But because it wanted to conserve, because we need the universe to conserve everything, conserve mass and momentum and energy and charge and spin. So we want to conserve everything. So how did that work? Right, so a wave comes out. Let's talk about it. So a wave comes out. Let's talk about first, I'll explain to you the problem, the way I used to think. So I used to think it's a complete wave. It's a three-dimensional, not only a two-dimensional wave, it's a three-dimensional wave. It expands out of the screen and into the screen and to the right and to the left. It's a sphere. When it hits this barrier, it becomes two waves that now completely interfere with each other. It's two complete waves that completely interfere with each other. And they create these patterns. It's going to be difficult to aim it properly, but it's going to create these patterns, whatever, I don't know. It's going to create all these patterns so that you would have electrons showing up here. So the way I was actually listening to Feynman's lecture about this, terrible audio. So an electron detector here, and there's a bunch of there's electron detectors everywhere. But these will pick up electrons and the other ones do not pick up electrons. So you have at the center, I think there's nothing, and then you have a big detection, nothing, a big detection, nothing, and so on. And to the other side as well, big detection, nothing, big detection, and so on. So you have a bunch of detections. So the question is, how? Meaning, okay, so a wave comes, so this wave, this is all just one electron. This wave, now it's two waves, these two waves, and with multiple, they need to have multiple crests and troughs. So it's like, and they need, like, in order to have the complete pattern, you need actually many waves. Anyway, this thing is huge, but this is all just one electron. Not just that, a lot of the energy has gone in every other direction. So what's going on? And then it ends up showing up only in this detector or in this detector, never in two detectors and never missing a detector. It's really confusing, really confusing. Really, anyway, but how? The question is how. So if an electron is detected here, why is it not detected anywhere else? How does the electron, how does the wave, with all this entire mechanism, how does it know to show up here but not show up anywhere else in the universe? How does the wave collapse to exactly one spot? How? It has to communicate with the rest of the universe. This is actually a very important video, because this actually explains away entanglement. This is not a joke. This is probably one of the most important videos in the universe ever. This completely resolves this nonsense about entanglements. Let me explain. I mean, first let me pose the question. So that's the question. So that, and of course I was not sharing the tab. Oh my God, because of course I was not sharing the tab. Why should I share the tab? Sharing the tab is a terrible idea. Okay, anyway, so those listening, I hope you didn't kill yourselves. Let's talk about what I was saying. Oh my God. So I was saying, here we have the electron gun. Here we have the two slits. Here we have the screen with each cup is a detector. So we fire an electron. An electron theoretically is a wave. It's an electron wave in the quantum field, in the electron quantum field, as physicists call it. So it's a three-dimensional sphere that expands from here, goes everywhere. Some of this wave goes through the two slits and becomes two waves with multiple crusts. It's not a single wavefront. There's multiple wavefronts that you need to have in order to have this pattern. So you need maybe, well, it depends on just how far does your detection go. You might need, I don't know, 10, 20, 30 wavefronts. So, but it's just one electron. How is one electron so much? What's going on? It's like it's endless energy. And it knows to go through these two slits, not go anywhere else, or if it goes anywhere else, I don't know, somehow it always manages to end up in one of these cups. How? How? That doesn't make any sense. Nothing here makes any sense. The whole story is nonsensical. Anyway, so when this complexity of wave interference, when it ends up being picked up by one of these electron detectors, how does it know to collapse here and not collapse also here and here and here and everywhere, anywhere else that it expanded to? How does it know that? Also, you could ask, what about the direction, right? When we fire an electron beam, the way we fire it is these plates are positive, or maybe even this is positive, so that there's a differential, there's a voltage differential between, right? We heat up a filament, and this is all in a vacuum. This only works in a vacuum and probably in the dark. So you heat up the filament, and so the waves, so the particles always want to go this way. So how can you say that it's a three-dimensional wave? What do you mean it's a three-dimensional wave? It sounds like it's it's actually particles. It doesn't sound like it's a wave. When you look at a particle beam, an electron particle beam, it looks like a beam of particles. So why are we suddenly saying that it's a complete three-dimensional spherical wave? That doesn't make any sense. Let's change the name of the video, because this video is going to be just, it's not research. So I finally understand why we don't need entanglement. Why we don't need superposition. Maybe just call it superposition and entanglement are nonsense. Question mark. No, it's the answer. I mean, I pretty much have it. I mean, I'll explain it. Superposition and entanglement are nonsense. Okay. So, what are we up to? So this is the way, and this is already advanced. I mean, I'm already at this point, me thinking about this, I thought I was ahead of everyone. I would say this is already thinking ahead of everyone, because at this time, I don't need to say nonsense like the collapse of the wave function. I would never say words like this is the collapse of the wave function. I don't need to say that. That's nonsensical. Or I never use the word superposition. Entanglement, yeah. The fact that I needed to somehow come up with a magical explanation, yeah. That Einstein said this is God is playing dice, yeah, I had to say that. But here I'm going to resolve it today. It should not be an issue. Everything is going to make so much sense, right? Another thing I had to say was that this wave is detected as a particle. Well, that's a problem, because what do you mean it's a particle? A particle violates Heisenberg's uncertainty. And what does it mean for a wave to collapse into a particle? How? How does it do that? As Paul Sutter says, how? How does the wave collapse happen? What's the mechanism for the collapse of the wave? How does it do that? How does the wave collapse? Why does it collapse? What is this wave collapse? Wave function suddenly collapsing. What is that? It's nice words, but it's nonsensical. I listen to Paul Sutter. He's okay most of the time. He's interesting most of the time. So, all right, that's basically the question. Superposition is, what is superposition? Superposition is that they're saying, I don't know, at this point it's both a particle and a wave. I don't know what superposition is, but anyway, this collapse, this magical collapse, I could not, for me, was the only problem. That was the only problem. The magical collapse of the function of the wave at exactly one spot, that was too much. All right, so what's the answer? So let me tell you what the answer is. So I was watching videos about Compton scattering, of all things. I was watching a simple explanation of Compton scattering. I don't even remember what that is. Like, what is that? I don't know. I don't think I was even paying attention to what exactly it is. I was just watching the derivation of the equation, and it was so mechanical. And I said, wait a minute. Wait a minute. So here's the explanation. The explanation is the following. It's very similar to what we did above. Let me put that, I'll put it here. Okay. It's going to be very similar. So we're going to have an electron gun. We're going to have, again, two slits. The two slits experiment. And we're going to have the screen. Everything is going to stay the same. However, when we fire an electron, so what is an electron? So an electron is not a complete wave. That's the secret. An electron is a partial wave. Now that's something that I don't think we ever see. We never see, like in a bathtub. In a bathtub, we're not going to make a partial wave. Something like this. That just travels. That just travels. Usually it would be a complete wave. It would be two-dimensional if it's a surface wave, or it's three-dimensional if it's like a sound wave. So when it comes to particles, they are three-dimensional, they are spherical, but partial. They're not a complete sphere, they're not a complete wave, they are just a part of multiple spheres. So you have to, when you fire an electron, it's just a bunch of waves. There's no membrane around it, and it's three-dimensional. So you have to think about it that it's three-dimensional. It's an arc when you look at it from the top, but it's also an arc when you look from the side as well. Whatever cross-section you take of this thing, these are all arcs. That is a particle wave. It's a particle wave. It's something that we don't usually see, but it's something we can imagine. Certainly with the help of a Fourier, it's something that we can create with the help of Fourier. Fourier allows us to create any waves that we want. And this, you can already see, this is why Heisenberg's uncertainty principle applies to this. Because, right, this is going to explain basically, I mean, I'm not going to say everything, but it's going to explain a lot. So much that I don't understand why Einstein came up with this idea. Turn off notification from Microsoft Store. We noticed you haven't opened these in a while. All right. So this is basically the idea of a photon from Einstein. So Einstein said in one of his later years, he said, I still don't understand what a photon is. Why don't you understand what a photon is? It's really very straightforward. Since we know how to create any wave using a Fourier analysis or Fourier transform, or using Fourier. So Fourier said you can create any wave. If you want to create this wave, you can, just by the addition of, I've never explained Fourier addition. You can take just a bunch of different waves and add them so that they all cancel out on both sides and they all add up here so that it's basically zero everywhere. except for at one, basic location. So this is now delta x. This is the location. So the more, the smaller delta x, and this is the frequency. So this is delta f. I don't know. This is the frequency that you have to use. So the sharper you want this thing, the more localized you want this wave, the more you need to use frequencies. The more you add frequencies up. A single frequency, just one line, a single frequency is an endless wave. So delta x is maximum. Delta x is infinite, is infinity for single frequency. And frequency is energy, because energy is hf. F is frequency. So this is energy. And energy is momentum. You can relate energy to momentum because, what is it? Well, E equals mc squared. E equals m squared mc c to the fourth plus p squared c squared or something. C to the fourth? I don't remember. And this is e squared? I don't remember. But you can convert, you can get p from e. So there is a relationship between p and e. So this is maybe that you can, this is delta p. So this is the relationship of delta p and delta x. Don't remember how exactly you derive Heisenberg. But okay, copy. Let me just, anyone who wants to join us is welcome. This is pretty remarkable. Okay. So back to this discussion. So a wavelet, this wave particle, this never changes. This is always going to be the particle wave, always. It's never going to collapse. It's just that we can never detect it, right? We let it go. This thing will go through both slits at the same time because we're aiming it, because of the way we're aiming it. So it's always going to go through both slits. Now, you could argue that some of it is going to impact the slit. So that's impossible because this is a single electron. So the way nature works is that you can never have half an electron. That's the trick. So this thing will always either make it through the slits or not. That's the trick. It's going to always stay intact or impact and get absorbed by the double slits. But if it doesn't get absorbed, then it's going to go through completely. That's the way nature works. Why is that? It probably has to do with the fact that the double slit itself is also a wave. This thing is also, don't forget, this is also a wave. This is a wave. Everything is a wave. So It's really not that difficult for the electron to go through the barrier. I mean, there's protons here, but these protons are anyway. That's well. I didn't promise you I understand everything. I just understand. I understand enough. I understand much more than yesterday. But this time, I don't remember if it was at this time yesterday. Yeah, I think it was last night. I was watching a video about Compton scattering. I should look at the history. I was just watching. I just said, let's just absorb. Let's listen to everyone about everything that has to do with quantum mechanics, just anything. And the more I listen to it, the more straightforward this thing is becoming. And there's no question. It's like, what is everybody so confused about? I don't even know what an alternative universe could look like. It's like, how would you want the universe to work if not the way it works, as I'm explaining? There's no dilemma, there's no magic. Everything is, you know, almost certain, very mechanical. Okay. Yeah. So, what's going to happen? Let me take an invite and copy it and share it also here so that anyone can join us. Anyone from the outer Welt can join us and tell us that we're wrong. Anyway, so this particle wave, it's not a particle wave duality, or it is. It's not either a particle or a wave. It's a particle wave. You could call it a wave or a wavelet. It's not a normal wave. A normal wave doesn't always want to stay as one unit. A normal wave, some of it can impact on the surface, and some parts will go through, and you'll get half an electron going through, and half of it got absorbed. But apparently, the way nature works, there's no such thing. And an electron is either it's completely absorbed here, or it's completely absorbed by one of the detectors at the other side. All right. Okay. So this wave is going to, I think it usually goes through. I think it's because, I don't know if they say this, but I think that this plate is positively charged. Well, how else would the electron, why else would it want to reach this plate? And this is neutral. So it doesn't want to, the electron doesn't want to stay here. There's no reason for the electron to stay around. The electron wants to fly through it because it's like 20,000 volts negative, and this is 20,000 volts positive. The difference between is like 20,000 volts. It's huge. Okay. So the electron ends up, of course, it's going to go through both slits. It's a wavelet. Because of the size, the question is, how big is this electron? Shouldn't it be really tiny? How could it be going through both slits? I don't know. Because when the electron ends up being around an atom, I mean, it ends up being an atom, then it's really tiny. It's really, really tiny. But as it's going through the slits, it's huge. So I don't know why when it gets to the atom, to the proton nucleus, it shrivels up for some reason. Or when it's inside a wire, the wire is tiny. And apparently there's trillions and trillions of these tiny particles. But when it's free to fly in a vacuum, it's huge. So I don't know how that works. I don't know how that works. It is weird. But you can understand, I mean, when there is no positive nucleus, nothing causes it to shrivel up. But when it's free to fly in a vacuum, then it expands to its maximum size. Don't forget that this is an electron of a certain frequency. No, all electrons have the same frequency. So an electron always have, we can measure the frequency of the electron. We know this is measurable. If we know, because we know the distance between waves, we know the wavelengths of this, of how it shows up, this distribution. This gives us an indication of this wavelength. So we can figure out this wavelength from this wavelength. There is a geometrical relationship. So we know there's a lot of stuff we can figure out about what this looks like. Anyway, so the electron goes through both slits and becomes two waves. Apparently that's allowed. It becomes two waves, two wavelets. Not complete waves, but wavelets with an interference pattern. So it becomes some sort of interference. Maybe it has an interference pattern, but it's still a wavelet with an interference pattern. Now this wavelet, right? It's the same energy, the same amount of energy, but now it's waving a little. The waving is a little bit different. Also, it could change direction. How can it change direction? Right? Because of conservation of momentum, it should not be able to just change direction. Okay, that's a good question, but it is able to change the direction. I don't know. A lot of it I still don't know. Anyway, but this thing ends up traveling and being detected as a single electron in one of these detectors. And it can only be detected by one of these detectors. It doesn't grow. Wherever it interacts as an electron, it's just like it went through both slits. When it gets detected, it's as one electron. Cannot spread over two detectors. because of the way it interacts with a detector. So it cannot, because of conservation of energy, of charge, of everything, it cannot be detected by two detectors. Now, isn't that magic? A little bit. But we no longer have this issue of entanglement, because wherever it's going to go is already determined by the time it interfered with itself. This interference at this time, it's behaving just as if there was a normal wave here. It's behaving just as if there's a normal wave that is interfered by the other wave. So some people sometimes are watching us. Anyway, the point is that this wavelet has a direction already at this time. This thing already has a direction. This wavelet. It's not that this thing crosses the known universe and then has to collapse to one spot. No. This thing is traveling to exactly one location. It has a very precise direction. Now, we cannot know where it's heading. There's no way for us to know where it's heading, because any detection causes us to basically absorb it. Wait a minute. Hold on. So they said that's not true. They said that they put a light source here. And when they put a light source here, let's talk about an issue. Maybe there is an issue. Okay, let's create a new guy. Okay, so this is, maybe we have an issue. All right, so maybe we have an issue. Oh my God. Okay, so maybe we have an issue. Namely, let's start over. So we put an electron gun here. Let's put a simple detector here. And a screen here. All right. And then they put a light bulb here. They put a light source here. So that when the electron zoomed by, it ended up being noticed, and then it decided, and then it collapsed. Because of the light source here, let me change the light source a little bit. So the light source is basically here. They put a light source here. No. No. Wait, I can magnify it. Oh. Oh, hamburger! Can you
Hey,
hear me? How are you, hamburger? What's
I'm
up?
good. Hey, how
Hey,
you doing, science?
yeah, I'm doing science. I'm trying to figure
Yeah.
out what. What are you saying? Can you hear me?
Yeah, I can hear you. I
Hmm.
wasn't saying anything.
What?
I didn't say anything.
Oh, okay. How's your throat?
It's better, but my nose is so congested I can't breathe, so I'm like really pissed off.
Uh, uh,
Like that's like genuinely like worse, and like it was kind of both at one point, but like
you know
you
your
know,
audio. You know your audio is not perfect. I mean, it's difficult to understand you.
other people haven't said that. I don't get that. I've been in other rooms today.
No, I have to guess what you're saying.
I wonder why.
Here, let me play. I have to guess what you're saying.
I wonder why.
Here, let me play. I have
I
to
feel
guess
like
what
that's
you're saying.
clear.
What? Wait, what? Here, let's do.
I feel like that's clear.
You feel like it's clear?
Yeah.
No, compared to my
Like I
voice,
can hear what I'm saying. Like I can understand what I'm saying.
you can understand. Well, some of the time, maybe when you try, but when you don't try, I cannot tell what you're saying. Oh, she left. Oh my God, she left. I think she has connection issues. Anyway, let's put a light source. I just want to put a light source right in front, right here. I want to put a light source. Okay, so we have, ladies and gentlemen, we have a light source. Okay, so there's a light source. Now I see the problem. The problem was that this thing is not centered. This is a little bit better now. Okay. So we're firing an electron. So why does it collapse? So when we fire an electron in such a case, it doesn't go through both slits. It goes through one. Why is that? So so it's a wavelet, but it seems to interact with this wave, right? A light source is a wave, so it's no longer a vacuum. It's no longer a dark vacuum. So the electron wave now interacts with the electromagnetic wave. An electromagnetic wave, we know that electrons interact with electromagnetic waves. It's a light source, so the light is always on, so it's waving. And a light source is actually an electron, or many electrons are waving, are jumping around in the light source. So the electron is interacting with this system. So that's not like the barrier, the slit, the double slits. The double slits, it doesn't interact with them. I don't know what they're made of. I think it's just a piece of paper. It's neutral or plastic or who knows. Might not even be metallic. Maybe if it's metallic, we wouldn't get the double slit experiments reproduced. So I don't know what it's made of, but I think it's neutral. So when you fire an electron, it's a wavelet, but when it gets to the light source, it interacts which means, it's basically like, okay, it was detected, so it collapses. It's fine for the electron to collapse. There's no violation. The wavelet collapsing into a nanoscopic object, there's no violation of the speed of light, of conservation of anything. There's no violation of conservation laws. And there's no violation of the speed of light. There's no magic in a collapse of a wavelet into a tiny particle. As long as Heisenberg's uncertainty is not violated, and as far as I know, I don't know, I mean, it's not violated. So there's no violation, so it collapses into a tiny, tiny, what looks like a particle. It never becomes a complete particle. It's always a wavelet. When it's free, it's a big wavelet. But when it collapses, it could become a tiny, tiny, tiny nanoscopic wavelet that we cannot see, not even with a microscope. Otherwise, it's big enough to go through two slits with huge lambda, huge wavelength. Okay, as far as I know, I mean, I don't even know. As I told you, I've never seen the setup for the double slit experiment, the electron double slit experiment. I don't even know what barrier, what double slits we're talking about. What size are the double slits? Okay. So there's no issue. So the title of this drawing is maybe we have a problem. I don't see a problem. I don't see a problem. So it collapses. When it hits a detector, it collapses too. And there's no issue. There's no problem in a wavelet collapsing locally. The problem used to be that a wave, a 3D wave that is the size of the universe, collapses. Sometimes it collapses inside a part. It collapses inside a black hole, and then we violate the speed of light. Because how does it know not to collapse simultaneously outside of the black hole, or maybe inside another black hole? I think this is what EPR is about. ER equals EPR, whatever, which is supposed to be Bell's theorem. So I think we need to look into Bell's theorem, but I think we resolved Bell's theorem. So the next thing is to look into Bell's theorem. I finally need to face Bell, because I've avoided Bell. Everything started that night when I was debating Mandible. So everything started with Bell's theorem. So I've avoided Bell's theorem because I didn't know, because it was never the issue. The issue was everything else. But now I'm wondering if I have a solution for Bell's theorem, because it looks like everything else has been resolved. Anyway, so there's a wavelet. So a wavelet comes out and interacts with the light. And because it interacts with the light, it shrivels and goes through only one slit. This slit or the other slit. Sometimes it goes through this one, sometimes it goes through that one. Well, that makes sense. Why am I having deja vu? Jesus, it's like I was here before. Nice, very nice. Okay, so that answers that. So that's it. So the next thing is to face Bell. Let me see how long have we been here. 55 minutes. Okay. I think anyone watching this should be blown away. This is so simple. This is so simple. We no longer have the issue of entanglement. The way I understood it, I had an issue with entanglement. I don't know if anyone else ever had that issue with entanglement. I did, because I had a wave the size of the universe, beyond the visible universe, that could collapse inside a black hole. And how did it know not to collapse simultaneously outside of the black hole? How did it have intelligence? But now I don't have an issue. It can't go both into and not into a black hole, because it's always kept intact. The universe doesn't allow for an electron to be broken into two half electrons. It's either a full electron or nothing. So, and there's conservation of particles. So there's a conservation of an electron. So an electron can never be lost from this universe. Okay. So I'm happy. I don't have a problem. So this resolves the collapse of the wave function. I don't have a problem. I have a purely mechanical explanation, not a complete one, because we need to deal with the momentum. How is there a change in momentum? There's no conservation of momentum yet. We need to figure out conservation of momentum. I mean, how could some electrons end up completely off to the side? We fire them straight and they end up. So sometimes they end up far, far over there. How is that possible? So it looks like they got a kick. But how could a wave get a kick? So you could say that the universe sometimes gives kicks. But is that allowed? Well, other times it's going to give it a kick in the other direction. It's completely random. These kicks are random. Well, they're not random. They're based on the double slits, the interaction of the two slits, so that it ends up being right. It ends up being and right, there's only this path and this path. There's certain paths that are allowed and certain that are not allowed. But what gives the particle wave, what gives it a change of momentum? So right, because the electron has a momentum. What action equals reaction? What did it lean against? What force, right? What gave it something needed to? Where did the momentum come from? Something. F equals ma. And, an electron has a mass, but it's also a wave. It's a wavelet. A wavelet does not. How does a wavelet have a mass or Energy is easy, but mass and momentum, how does a wave have momentum? Well, it has momentum because it has energy. E equals hf. It has energy because it has frequency. So it has energy, so it's equivalent to mass. Is that the reason? I don't know. So there's still a dilemma around that. But there's no, it's okay for the universe to give it a tiny kick. It's a tiny kick. It's a tiny, tiny, tiny kick that the universe endows the electron. But because it's random, later the universe will take it back when it's going to kick the next electron the other way. So the universe in general gives random kicks. The average energy is zero. I mean, the average momentum is zero. So the universe has an average momentum of zero, but because it has quantum fluctuations, it's allowed to give tiny kicks in all different directions. That's fine. So there's no violation there. We're allowed to give tiny kicks. I think it's also within Heisenberg's limit. So there's no issue there. But the point is, there's no spooky action at a distance. The wavelet has always traveled in a certain direction. It's not that it's magically collapsing. It doesn't have to decide to collapse at any point. It was always traveling from its inception. Right, let's say it ended up over here. That means it was always traveling. It was always traveling this way. So we don't need to collapse the wave function at this time. The universe doesn't have to collapse the wave function over here at this time, at this place. The collapse never took place because it was always collapsed. The collapse is just our way of asking, okay, given a detector, what is the probability that the detector will detect an electron? Just that's it. That's what Schrodinger's wave function gives us. That's all. There's no collapse. There's no wave function. It's not even a wave function. It's a heat function. It's just a function that predicts the probability. It doesn't even predict. It just tells us the probability. It's just a summation of the data. But the universe doesn't have to decide. There's no deciding that violates the speed of light or intelligence or anything weird. The decision to take a certain direction took place right when it interacted with itself. Right when it became two waves and these two wavelets interacted with each other, then it decided to become a wavelet in a certain direction. I don't know how that works. We'll come back to that, but there's no longer an issue of I don't have a problem with this weird collapse of a wave function. So the next question is Bell's theorem. Can I explain Bell? Isn't there a problem with Bell? Bell says no hidden variables. This sounds like a hidden variable. It sounds like the decision what is the direction of the wavelet? Sounds like that decision was known right when the electron crossed the slit. So, okay, we'll have to look at Bell's theorem. But I think Bell deals with electron pairs. We never dealt with electron pairs. The question is, will Bell have anything to say about this experiment? Did Einstein have anything to say about this experiment? Or did Einstein only just have a problem with the Stern-Gerlach? Is the Stern-Gerlach the only issue Einstein had? Or did Einstein, I mean, Einstein is my my benchmark. Like Einstein, right? There was a big disagreement between Einstein and Bohr. Bohr said, shut up and calculate, or God, don't tell God what to do. And Einstein said, God doesn't play dice. The question is, did they have this disagreement over the double slit experiment? Or did Einstein have a good time with the double slit experiment? What did Einstein, what was the situation? Okay, so let's look it up. Let's look it up. Let me take a sip of water. But this is, for me, this is a major, major milestone. A very, very big milestone for me, because when I started on this path a month ago, approximately, like the double slit was a major issue. Then I said, okay, everything is a wave. But then I had a major issue with the collapse. The collapse of the wave function was magical until yesterday. I no longer have an issue with the collapse of the wave function. Okay. So the next issue is, I guess, Stern-Gerlach. That's the next issue. Stern-Gerlach and Bell's theorem. Bell's theorem, I think, is only, is it? Bell's theorem is about entangled pairs. We need to learn about entangled pairs. So there's no entangled pairs in Stern-Gerlach, and there's no entangled pairs here. Okay, so we need to look into entangled pairs. Oh my God, this is so difficult. Difficult and easy simultaneously. Interesting and boring simultaneously. That's the big trick. Okay, so now we need to look into, okay, I want to read, did Einstein have an issue with the double slit experiment? So did Einstein have issue with the double slit electron experiment? Electron experiment. Albert Einstein did express concerns about quantum mechanics, which are closely related to the implications of experiments like the double slit experiment. But his objections were more general rather than specific to the double slit experiment itself. Einstein making concern. Determinism. Probably Einstein famously had issues with the probabilistic nature of quantum mechanics, epitomized. So for me, quantum mechanics is no longer probabilistic. The wave equation, which is a misnomer, the heat equation, the Schrodinger equation, is probabilistic, just like the probability of flipping a coin. It has nothing to do with the nature of the electron. It's nothing to do with the nature of the electron. The nature of the electron is the nature of the electron. It's just a wavelength. There's no issue. Who is that? No, I cannot take the call. I cannot take the call. Let me just give them a message. I cannot take the call. 1 second. 1 second, please. Is it urgent? Everything is very good. We're moving forward. Okay. I cannot listen. Right. Please, if it is urgent. All right. Okay, so the question is very interesting question. So, okay, I don't have a problem. So I resolved the problem. Let me see what it says. Is that issue? No, not urgent. Okay. So I resolved the problem of the Einstein. The problem of the Einstein was the probability. I know. So my universe is deterministic. This was my main concern, was that the universe seems to be indeterminate. But now the universe is back to being mechanical. My universe is mechanical. This is great. I would not have been able to understand a non-mechanical universe. It's a very simple, straight, okay. All right. Okay, so Einstein famously had issues with the probabilistic nature of quantum mechanics, epitomized by his statement, God does not play dice with the universe. Yeah, I no longer have this issue. I had this issue, I resolved it. Why did Einstein not resolve it? That's weird. He was uncomfortable with the idea that quantum mechanics only provides probabilities for the outcomes of experiments rather than definite predictions. Right, and the way Feynman, I was watching his video, his lecture, and he said, this gun is shaking. So you're getting a probability already from the shaking of the gun. The electron gun is not stable. He actually pretended to hold a gun and to wiggle it around and to jiggle it around and to get kick. This gun is not precise. So you're already getting a probability from this imprecise gun, right? This gun, it's not like it has a super pinpoint heated filament. It has a gigantic filament, but you're heating up to 20,000 volts. There's nothing determinant about it. This is indeterminate. This is already probabilistic. This is where the probability emanates from. You cannot complain, oh, woe me, the universe is probably, no, the universe is determinate. It's not probabilistic. Your gun is probabilistic. Your gun is unstable. Maybe you can stabilize your gun, and then you'll get all the electrons going into a certain detector. I don't know. But the way Feynman explained it is that the gun is unstable. Mr. Feynman himself, he said that. And the way I understand the gun, it's an unstable gun. Okay, so we resolve that. That's resolved. Epitomized by his statement, God does not play dice with the universe. He was uncomfortable with the idea that quantum mechanics only provides probabilities for the outcomes of experiments rather than definite predictions. But there's nothing I can do about that. If your gun is unstable, what do you want? What do you want? Of course you're gonna get things going all over the place. You're flipping a coin and you're distraught that you can only predict the probability of flipping the coin. I'm sorry about that, but you're building a probability into your experiment, and then you're complaining that there's a probability coming out of your experiment. Well, it's totally up to you. So I don't see the issue. Wave-particle duality, the double-slit experiment, when performed with electrons, demonstrates wave-particle duality. Well, we resolved that. Electrons show interference pattern like waves. Einstein explained that in his seminal 1905 paper about the photoelectric effect. That's exactly where this notion comes from. He says he doesn't understand what the photon is, but I don't understand what he doesn't understand. He explained it actually very well. This happens to me actually quite a bit with Einstein. He explains, I understand, and then he says he doesn't understand what he just explained. I don't know. This happens again and again. Really weird. I don't know. So electrons show interference patterns like waves when not observed. No, it's nothing to do with being not observed. There's nothing to do. Of course, if this were the case, that would be bizarre. No, electrons show interference patterns like waves when they're moving, like when they're free to roam the universe, but act like particles when measured. Okay, I mean, when you interact. Okay, so, I mean, it's not like particles. It's, they shrivel. So what? So what if they shrivel? But they don't shrivel across the universe faster than the speed of light. They shrivel probably within the speed of light. The shrivel is explained within relativity. That's the main realization that I had yesterday, or even right now. The shrivel process is fast, but it's not a violation of the speed of light fast. So it's not like there's no issue that a wave collapses into a tiny, tiny, tiny particle-like wavelet. It can grow and it can shrivel. The energy can expand and it can, what's the opposite of expand? Shrink? Okay, so the energy, right, it goes from a big wavelet into a subatomic wavelet. That is incredible, that all this energy ends up being in such a tiny confined space. Sometimes it's able to interfere with itself across the double slit, so it's big enough to go across the double slit. But notice that the double slit is not big. It's not like you can have a meter between the two slits. In that case, I don't think right? There's a limit, and the limit is tiny. The two slits need to be very close to each other. Okay. So electrons show interference patterns like waves when not observed. Not that they're not observed, that's not correct. It's that the right. It's not observed. We could leave them alone in the room if there's light and air. Then they're not going to go anywhere. First, you need a vacuum, and then you need dark. If there's light, we know that it causes the shriveling. It's going to shrivel. I wouldn't say even collapse. You could say collapse, but you could also say shrivel. Collapse sounds like woo-woo a little bit, especially collapse, like collapse, whatever. It's a collapse within known physics. There's no violation of known physics. The collapse of the wave function sounds like that is bizarre. That whole thing is bizarre. But a collapse within the known laws of physics, there's nothing weird about that. So electrons show interference patterns like waves when not observed. It's not correct. Under certain conditions, they behave like waves, but act like particles when also not true. In other cases, sometimes they behave and sometimes they behave. It depends on what. I mean, when you interact with an electron, it shrivels. If it has a reason to shrivel, it will shrivel. It shrivels when it goes into the nucleus. And when it wraps a nucleus, a proton, it shrivels. And then if it comes out, we don't even know if it's the same electron. We fire an electron. It might be that electron replaced another electron, bumped out another electron from the nucleus, and the other electron is now flying. We don't want to have personal identification for each electron, so we don't know. They're all interchangeable, so we don't know which is which. So, but it doesn't matter. So I don't have an issue with that. This duality was one of the quantum phenomena Einstein found troubling because it contradicted classical intuition. So I don't have an issue with that anymore. For me, it's completely classical. It's completely mechanical. The particle wave duality for me is completely mechanical. I don't have an issue with that anymore. Jesus, I've come a long way in a month. Quantum non-locality. Although not directly about the double-slit experiment, Einstein's broader concerns about quantum mechanics included issues with non-locality, as illustrated in the Einstein-Podolsky-Rosen. This is the EPR paradox. The EPR paradox has to do with a wormhole, which I don't think they exist, but but this is Bell's theorem. This is what Bell's theorem supposedly contradicts. This thought experiment highlighted what Einstein saw as spooky action at a distance, a feature of quantum entanglement. So that's when you get a pair of electrons, and supposedly there's no hidden variables allowed. We'll see. That seemed to violate the principle of locality and causality. I don't know what they mean by this. We need to look into it. Double-slit experiment. How much more do we have to read? The double-slit experiment is a crucial demonstration of the principles Einstein found unsettling. When electrons or photons pass through two slits and form an interference pattern, it suggests that they behave as waves. However, if you measure which slit the electron goes through, the interference pattern disappears and they behave like particles. Yeah, you interfere with a system. The system is no longer the original system, and then you're coming to me to complain, oh, the system is no longer the same system. Yeah, you modify the system. What do you want from me? Why are you complaining? Why are you complaining so much? Stop modifying systems and complaining that the systems are modified. Stop it. Get help. as the famous quarterback. Was he a quarterback or running back? Used to say in the commercial. So, where are we? When electrons pass through, however, if you measure which slit, yeah, the interference pattern disappears and they behave like particles. What do you want from me? What do you want from me? What's the question? That's a mechanical effect. You're like, I had a mechanical effect on the system. Yes, you did. Next question. You mechanically interacted with a system. What do you want me to do? What's the question? I can't believe that. You want to tell me if I would have read this yesterday, it would have been still perplexing? I don't believe it. I cannot even understand the question at this point. Everything is so mechanical. And I was listening to Sean Lafessel, Sean something. Sean, it's like a famous Sean something. Sean from Berkeley. What's his name? He's writing all these books about quantum mechanics. He explains the wave. He explains that the universe, the particle and the detector become the wave. Everything is the wave. The universe is the wave function. Everything is the wave function. This guy, is he nuts? I was sleeping and listening, and that's why I barely slept. I was actually very comfortable sleeping and listening to this guy making zero sense. I'm like, this guy makes zero sense, and he's writing books and books and books and books and talking and talking and talking. Sean, what's his name? Sean Carroll. Professor Sean Carroll. Professor. 3 people are watching us. It's an honor. Anyway, so Professor Sean Carroll, we're going to have to do a video reaction to Sean Carroll now that I feel like a Jedi master that has to face a normal person, and I can just run circles around these people. This is such an incredible feeling. I mean, I know that but it's not normal people. These people, they're not Sith Lords. They are. It's like it's in the what do you call it? The Star Wars lore. They only have Sith Lords and Jedi knights and lords. But there's a different type. See, because you can become a Jedi Knight. You can learn quantum mechanics and understand it, I believe. And run circles around these professors who now, are they pretending? That's the question. They're not Sith Lords, because a Sith Lord, see, I can be a Sith Lord if I want to. I can fool anyone, because I've gained so much knowledge in quantum mechanics and relativity. So I can be a Dark Lord if I want to. How would I be a Dark Lord? I don't even know how I can be a Dark Lord. Like, I can just say nonsense, but then I'd become one of them. The nonsensical ones. I guess that is a Dark Lord. I guess they are all Dark Lords. They're all liars. Was Einstein a liar? I don't think so. I think he was openly perplexed. But all these dark lords, they're not openly perplexed. Sean Carroll is not openly perplexed. He never says, I don't know. He always says, the universe, there is a, what do you call it? There is a wave function for the universe. What? What is he talking about? What, I don't know what he's talking about. The wave function is a simple function to give you the statistics, the probability of a coin, of how many coins are gonna be heads and how many tails, or dice, how many this. It's just a probability. It's just, it's based on data. It's just the data, and the data is mechanical. It's just a mechanical explanation of how wavelets, particle waves behave. They behave in their own way because they live within their own universe. It's a different kind of universe than ours. We are in a more continuous universe, and the little guys, they live in a universe that is discontinuous. Like, we can split everything in two, but electrons cannot ever be half electrons. A photon can never be half a photon. So because they cannot split, that's a different universe than we're used to. We're not used to not being able to split things. This goes back to Demokratos, that he said that at the end, you end up not being able to split things. So that's when, but Demokratos never realized what are the implications of not being able to split. The implications are quantum mechanics. He could have, so could he have thought, can you figure out quantum mechanics from a thought experiment? It's a good question. It's like, can we, given that apples fall from trees, can you figure out gravity? Yes. From gravity, can you figure out quantum mechanics? Yes. Okay. And then, can you predict, well, would you be able to predict a photon, an electron? I don't think so. I cannot right now. But given photons and electrons, I'm beginning to be able to limit their behavior to what we see in the data. So there's, at this point in my mind, there is a lot of parallels, a lot of match between what my thought experiment of a photon and an electron, and what we see in the lab. Incredibly enough. All right, let's continue. So let's read. So this wave particle duality, and the role of the observer, there's no role of observer. There's absolutely no, in determining the outcome, I don't even know what you're talking about. What? Where is there a role of an observer? There's just a role of interaction. But many people have said this before, yet ChatGPT still, so many people are saying this nonsense that ChatGPT believes it. So of the observer in determining the outcome were, oh, someone has joined us. I wonder who has joined us. Oh, Senes, what's up?
What's up?
Are you listening
Yeah, yeah.
to the great?
I
So
was listening,
are you completely blown away?
but I mean, I wasn't listening that much.
Oh,
I just turned on the stream.
oh. So at this point I'm done with quantum mechanics.
Really?
Basically, I understand why there is no entanglement. I understand the collapse of the wave function. It's
Oh, okay.
completely,
So
yeah, it's very simple. Everything is very simple, very mechanical. I don't need any violation of the speed of light. I don't need to violate any classical mechanics. It's completely classical. So the double slit experiment is completely classical.
yeah. So what did you conclude? How does it work?
So how does it work? How does it work? So let's go. I'll do the drawings. Let's share this. I was just reading. I was reading because I'm now trying to understand. Okay, what am I still missing? So did Einstein have an issue with the double slit electron experiment? Because I'm trying to finish all the corners, finish up with everything. I'm just trying to dot all my I's and cross all my T's. I just want to make sure that I'm not missing anything.
Mhm.
So as far as the double slit experiment, it's completely mechanical. That's it. I can explain it completely using classical mechanics. So let's do it. It's really, really very simple. You're not going to believe it. So the whole thing, so I realized, so I was watching last night the derivation of Compton, or the explanation of Compton scattering, whatever that is. And it's not important. It's just when I was watching it and I was watching the derivation, so I felt like, wait a minute, they're treating photons and electrons like tiny wavelets. So why am I confusing myself with these complete waves? If I just treat everything as wavelets, I'm done. Quantum physics is mechanical. So that's all you need to do. So until today, I was always thinking, let's start over. So let's start over with a double slit experiment. You watching my thing?
Yeah.
Okay. So here is the electron gun. So I was always thinking, all right, every time you have an electron coming out, it's going to be a three-dimensional wave. Three-dimensional, it's a sphere, it's a single sphere. And it's going to go through the double slit and then impact on the detector. So it's going to end up as two waves. And it's going to end up being detected by a single detector somewhere. But how? Wait, I need you to choose a different. But how? How did it? How does this wave, right? This could be the size of the visible universe, or even beyond the visible. This could be the size of the entire universe, beyond the visible universe. So how does the electron know to be detected here, but not here? How?
Does it really
So,
happen?
what do you mean? I'm assuming it has. This has to be true, because you always have double slits. You always have electrons. You don't even need to have a double slit. You can have a single wave of an electron going through the universe and then being detected by, right? You could have one detector here and another detector on the other side of the universe here. This could be inside a black hole. This could be inside another black hole. How does the electron know? How do you get conservation of conservation? How do you maintain conservation of anything? How do you not get multiple electrons? How does this electron know to show up here, but if it shows up here, it should not show up here? Who manages the universe? Who keeps track of who does the accounting? The universe needs an accountant that needs to be intelligent and needs to make sure that electrons don't show up don't violate conservation laws. Right? So I don't need an experiment to ask this question. Wait, what just happened?
Might have been mine. I don't know.
Oh, okay. But do you understand the question?
Yeah.
Right? So that question that I'm asking, it's not only in the double slit experiment, it's always true. The fact that it comes up in the double slit, well, it comes up in the double slit, but it comes up even without the double slit experiment. It's the same question. How does the universe not blow up or not disappear? Who does the accounting, and how does he do the accounting? This accounting needs to violate the speed of light, the cosmic horizon of the universe, black holes. There's so many violations. How does it work? Especially the speed of light. Since we believe in the ether, me and you, we believe in the ether. The ether puts an extra constraint on our heads. We have a much harder limit of the speed of light, which, Einstein, now I have even more respect for Einstein, because he lost his mind. He said, right? He went home and he never came out for 40 years. He said, I gotta figure this out. This doesn't make any sense. It took me just 20, whatever. It took me less time than him. I don't know why.
Okay, but continue then.
Okay, so what's the answer? So the answer is, as Einstein explained in his photoelectric effect paper, it was never a wave to begin with. This never happens.
Yeah.
This cannot happen, because this is already a violation of conservation. There's too much energy in here.
Yeah, that's true.
So what is an electron when it moves? So an electron, when it moves, is something that I call a wavelet. It's not a wave, it's not a particle, it's a combination. It's a wave particle. It's mechanical. It's something that we usually don't see, but it's possible to create it because of Fourier. If you use Fourier, you can create anything you want. So here is an electron. It's just a wavelet. And I'm going to put a boundary around it. There is no boundary
that's
around
how it supposedly works. Yes, but
exactly.
then you have the results. The double slit experiment that sometimes you get
Everything.
and sometimes you get bored.
Exactly. Everything is explained through this, but this is mechanical because of Fourier allows this.
But the weird result is not that. Is not the interference. The weird result is like when you make the measurement, you stop the interference.
Wait, wait. So does this answer all the questions, or do you still need me to go through the double slit experiment and explain it mechanically?
No, this answers why there is interference, right?
Sure. So
That's
what's
not difficult, but
okay?
The real question is when you make a detection,
Yes.
right?
Yes.
You then get the interference pattern disappears.
So the question is, what is a detection?
Yes, of course, that's the key. So have you figured that out?
I don't know what a detection is, but whatever it is, right? We know that sometimes an electron is big enough to go through macro double slits, right? The double slit experiment is a macro experiment. It's in the real universe.
Mm-hmm. Yeah.
So we know that an electron is big enough to go through macro slits and end up interfering with itself.
Okay, what about when you make the so-called measurement?
No, wait, hold on. Let me, we'll get to it. But there's we need to do, there's still a question before the measurement. The measurement is simple. The measurement we don't know what the measurement is. I'm assuming, so here it is. I'm assuming the measurement detector, ultimately there is a proton that's waiting for it, right? It's positively charged. Otherwise, why would the electron travel, right? There is 20,000 volts differential in the electron double slit experiment.
Okay.
So the electron wants to go somewhere, so there's a proton waiting for it. So we know that electrons end up as nanoscopic objects. They end up shriveled. They end up shriveling. They become shriveled when they interact with a proton. So it
Well,
becomes.
that works with light as well. So that, but that's just
We
like
can
no, usually those detectors they're like either like photographic film or some kind of noise amplifier.
look. It has to be. It's positively charged. So there's a proton without an electron, and this electron
Can
is
be,
going
yeah.
to end up what?
It can be, yes, can be that.
I don't know. I mean, you tell me. You need to tell me what your detector is, and I'll
Yeah,
have
it's
to
usually
think
photographic film or some kind of noise
what is.
amplifier thing.
No, no, no. It cannot be with an electron. Nothing. I don't think photographic film maybe is with a photon. An
Yeah, photographic
electron.
film with photon, but yeah,
So
with
we're
electron
doing.
it kind of works as
We'll
well.
co-
They
we'll
have
come
like
back.
noise things.
I don't know what that is. Look, as far as I know, it's some sort of positively charged detector,
It could be
and it's connected so that when it becomes neutral, you'll notice it. That's all. You're gonna notice when it becomes neutral, when an electron is gonna end up wrapping itself around this proton. You'll notice it. That's what a detector is. So, but the question that I still have a little bit, it's a tiny question, is what about conservation of momentum? This electron was going this way, and now it's going to go that way. So there's no conservation of momentum. Something the universe gave it a kick that way. So where did the kick come from? That's the question. Right?
hmm
So that's not a problem. It's not a problem
That's not too
because,
much of a problem. No,
wait, what?
that's not too much of a problem. No,
Yeah, correct.
that's just
It's
wave
a,
mechanics, really.
exactly. It's quantum fluctuations, it's Heisenberg uncertainty, it's borrowing momentum. It's allowed. And it's
No, it's
random.
okay.
So
And even these detectors, they sometimes they detect, sometimes they don't. It's nothing special.
okay,
It's like you can imagine this as a even when it's one electron, you can imagine it as like as you're doing like as kind of there is a compression and there's like constant compressions and distensions within the electron because it's going at it's pressing against the medium, so to speak, and then it's compressing the medium, it's attracting, then it's repelling, it's attracting, then it's repelling. It's kind of like that.
you mean the ether? It's waving through the ether?
Yeah, yes, can be the ether, but it's like if the ether is composed of different charges, then it will attract positive charges, and it will pass the positive charge, and then it will go into the negative charges, and then it will pass the negative charges, and then it will go into the positive. So it's like a waving behavior.
I don't think the ether has
Yeah,
charges.
it
I
has to
think
have because it has like it has like permittivity and permeability, so it's an electrical media. it's neutral at at a larger scale.
But the ether doesn't have these qualities that we perceive. We are creatures of the ether.
Yeah, there's that as well.
So I don't
But
think I don't think
like some kind of properties that are in line with charge.
I don't my intuition is that the ether just allows for different types of waves. An electron is one type of wave
Yeah,
and
it
a
can be that.
quark. I
So
think every elementary particle is a type of wave in the ether. It's a different way for the ether to wave. Anyway, so
if you have
everything
a
is
very
resolved.
small, if you have like a very small, very small cavities, then there
Very
will be
small
different effects
cavity.
that will be kind of random. It might go into many directions. So
A cavity? You said a cavity in the ether?
no, a cavity like in the experiment.
Cavity in the experiment? You mean the
Yes, and
detector?
then it will go, and then when you pass one of the cavities, it will go in all directions afterwards, and you get an interference
What do you mean
pattern.
cavity? You mean the slit?
Yeah, slit. Uh,
Okay.
so yeah, that's not that surprising. Of course, the thing that's weird is the measurement part, but that depends on what the measurement is and why it destroys the interference pattern.
What do you mean it destroys the it is the interference pattern.
No,
It
when there is
is.
a measurement, right? You know
This
what the problem is.
no.
No, okay. So I will give you a
But
YouTube video.
we're but we're talking about the electron double slit experiment. Don't
Yes,
confuse.
but there's that experiment that shows
Mhm.
that electrons behave like waves or behave like wavelets, as you said.
Oh
And
yeah.
then there's the experiment where there is a detection somewhere that makes it so that the interference pattern
Yes.
is destroyed. So you
Yeah,
get a
that's
false
not a
pattern.
yeah, that's not a problem. I explained it over here. You
Oh,
see,
okay. So what's the
I put
explanation for that?
I put a light source here and everything is explained. There's no problem. So here, let's do it here. So let's put a light source. I think they put it over here.
You can put it anywhere. That's the thing.
Yeah, but I think I want to reproduce the experiment. I don't want
Mhm.
to, as far as I know, they put it right here, right before the slit. Okay, so if you put it there, so as the electron is waving, right? So there's a light source here that is continuously on. So what are you saying? What are you telling me? So there is a filament here with protons and neutrons and electrons. There's a whole universe. There's a whole universe here. Of course, this electron is going to interact with this universe.
Yeah, that's obvious.
And then it's going to be re-emitted. Maybe it will be re-emitted. Maybe it's probably going to be re-emitted.
Yes, it
Maybe
has to be re-emitted. In
so.
fact,
If it's re-emitted, look, you're changing the experiment. You
yes,
have you have a very complex universe here. So
it
I
has to
don't
essentially
know.
like be stopped and re-emitted to some extent.
I
So,
mean, there's conservation of
like
momentum.
I think in electrons they use magnetic fields, right? Like that's what they use,
I don't know.
or they use
Look,
like electric field detectors or something too.
I don't know. Look,
They use,
they
I
have
think they do. They use like a magnetic field or electric field detectors.
no. I don't think there is a magnetic field. There's an
Or not.
electric
Like, okay,
field.
let me ask ChatGPT what they use to detect the electron.
No, to detect the electron.
Yeah,
How,
to make the measurement.
okay. Anyway, so I no longer have this collapse of the wave function that was so difficult. So now either an electron falls into a black hole or it doesn't. That's it. Like until yesterday, the electron was able to fall into two black holes simultaneously. Now it can't. I think this has to do with the EPR paradox. I think so. My next step is to look into Bell's theorem. I think that should be
What
it.
was Bell's theorem? Remind me.
I don't know. We never discussed it. Today, I was just about to start research on Bell's theorem. And before that, I just looked into ChatGPT, what ChatGPT thinks, what else bothered Einstein about the double slit experiment. I went through everything, and everything that bothered Einstein about the double slit experiment, I have resolved. So I'm fine with the, it's for me now, quantum mechanics for me is completely mechanical as far as the electron double slit experiment is concerned.
Yeah, they use electromagnetic field detectors. That's what they use.
Electromagnetic?
Yeah.
So they probably just shine a light. So when the electron hits the detector, it causes a light to flash. It releases.
Like a small magnet or something. Or it's like,
No, there's no. Why do you keep saying magnet? Why? It's just a light source. It causes the filament to flicker, and then you see a photon. That's all. You see a photon, or you have a voltmeter, or an amp, a current meter, or whatever. You have a voltmeter. You have some sort of a meter that measures that the electron has arrived, and you're done. It's really it's look either way.
It's an electrode, of course.
It's what?
It's an electrode.
Yeah, so it's very simple. It's basically as I surmised. As I assumed. So you have a voltmeter here, and the needle is going to go from here.
Just basically some conductive material, serving as an electrode.
You have
Like the most obvious thing.
It's going to jump from here to here, and that's it. You're going to have a detection. It's going to jump.
Okay, the question here is that this also works. I don't know if you know, but this also works if you put the detector anywhere.
What do you mean?
You could put the detector not even in the path of, not even in that path. Like you could put it after as well.
What do you mean? Look, I was watching Feynman. He has a 1-hour video where he discusses the setup. Finally, somebody's discussing the setup.
Okay, yeah, but there is another. You can like use a beam splitter in the middle, and then you split the beam to some other direction, and it still works.
I don't know. I didn't look into that.
No, but
Let
that's
me
important.
just.
Like,
Okay,
I
look.
think the Action Lab guy had a video like that.
But I don't know if you can do that with an electron.
Yeah, you can.
A beam splitter with an electron?
I don't know, but it works
I
with the
doubt
proton
it.
as well.
Look, it's not critical. I don't want to go through. I'm more interested in Bell's theorem. I want to see if I can figure out Bell's theorem. We'll figure once we understand. Look, Feynman says that the electron double slit experiment is the most important experiment of quantum physics to understand. If you understand that, you understand quantum physics. And I agree with him. So let me show you.
Bell's theorem is like the entanglement thing.
What? Yeah. Richard.
It's like the thing that. But that's just dumb. You know, like that comes from the Sterl-Gelbach or whatever experiment.
Yes, but we need to look into that. We need to be able to. Yeah.
No, that's just that's not really. There's nothing to it basically. It can all be explained by simple statistics. Distinti had a video explaining that with just simple statistics. It's not difficult. Like if you want to see that video,
I didn't really understand what you said. I'm
oh,
showing
Distinti has a video that explains that with simple statistics.
what Bayes, not Bayes.
Bell's
What's his
theorem,
name?
yes.
Bell's theorem. 1 second. Let me just show you this video. You see, he explains. He goes through. He really explains the mechanics of how they run this experiment.
Yeah, no, but I understand that part. The weird part is
No. No, you mentioned something about they can put the detector anywhere. He explains everything about this experiment, and let me
including that.
just show you. Yes, he talks about the detectors, exactly how they. Here is a detector. This is a detector. He discusses what a detector is, and not what it is, but he talks a lot. Look, it's an hour. It's 53 minutes. He wastes a lot of time, and the audio is terrible, but there's a lot of good
50 minutes,
information.
not 1 hour
I
and
heard
50
I heard things in this video that I never heard before. So this gave me a lot of insight. He answered a lot of questions that I had about the setup of this experiment. He explains a lot about the setup. Okay, so let me put a link to this in the VC chat.
Okay.
Okay, so what else? So let's look into. I was going to read just the end of ChatGPT. So the double slit experiment is crucial. Is a crucial demonstration of the principle Einstein found unsettling. When electrons or photons pass through two slits and form an interference pattern, it suggests that they behave as waves. However, if you this wave particle duality and the role of the observer, that's ridiculous. There's no observer in this discussion. I don't even know what they're talking about, observer. Einstein could never fully reconcile with his belief in a deterministic universe. So my universe is deterministic. I'm so happy. I mean, I don't care, but it's it's back to being deterministic. Like yet last night it was not deterministic, now it's mechanical. In summary, while Einstein did not specifically have an issue with the double slit experiment alone, the phenomena it reveals, wave particle duality, the role of the observer, and the probabilistic nature of quantum mechanics were central to his broader discomfort with quantum theory. Now, we don't have an issue. Notice that we resolved the issue of Schrodinger's equation, right?
We solved that.
Right. So Schrodinger, like until last night, was how does the electron know to show up here and not there, not anywhere else? Like, but now I don't have this issue. Okay. So you want to look at this video?
Which one? The one I sent?
Yeah? You want to
Yeah,
look?
okay.
You want me to look into it?
Hi, welcome to the quantum entanglement fraud. This is
You don't want to look at
He goes into it right away.
you don't want to look at Bell's theorem first?
That's Bell's theorem.
But okay.
video. I'm going to show you that the quantum entanglement experiment, as given by the Bell inequality experiment, is complete bullcrap. It can be explained with ordinary causal physics. And in this video, I'm going to demonstrate a simple computer simulation that the source code and executable will be published for free for everyone to see for themselves. Okay, and this is very important for my Patreon people to understand that I have to spend time in this. I'll explain that to them toward the end of this video. I would like to thank the YouTuber Karma Penny, related to extremefinitism.com. His video is the only detailed video of the Bell test inequality experiment. All the other videos I looked at, they're just kind of these general overviews and they don't explain the little details very well. little details like, what is coincidence detection? What do they mean by like 80%, 85% this, and 25% that? He did a very good job. I recommend you go watch his video. And his video is also a debunking of entanglement. I think in the end, we're saying the same thing. Okay. He uses probability, he uses hidden variables and the concept of the photon, where I don't agree. I don't believe in photons. I use a simple wave mechanics and I use linear.
Yeah, I used to also not believe in photons, but now I definitely believe in photons. There's no difference between a photon and an electron. They're very similar.
Polarizers, the way we did them in video T7. And I show using a very simple engineering simulation that you can get the same answers that they got without entanglement. Okay, so I recommend you watch both of them. I'm pretty sure they're both saying the same thing, but the simulation shows a little bit more, and I'll explain that a little later. Just to recap, in the trailer video T8, I demonstrated that the particle wave duality was nonsense. Physicists were treating the corpuscular nature of their detection device as the corpuscularity of light. In other words,
If he's going to deny the results of the double slit electron experiment, then that's ridiculous. I mean, it's been it has been reproduced on YouTube.
No, that's not a double slit experiment.
What do you mean?
What he's doing
He's
is not a
showing-
double slit experiment.
Look, he's showing the double slit experiment over here.
Well,
This is the
oh,
double.
that's
This is the
in T8.
this is-
That's
This is the electron double slit experiment. I demonstrated that the particle wave duality. He
oh,
says
he has
there
a
is no-
video on that as well. But that's like we can watch that video after. But
No,
that's
but-
just a side note.
Fine, but I'm just saying, if he's gonna disbelieve in
Yeah, it demonstrates how the instruments work and
No,
basically what
but
he's saying.
listen,
the spectral flight is
listen
smaller
to
than
what-
the nebulous.
listen to what he says. No, he's going too far.
the simulation shows a little bit
I mean, I used to also agree with him that the double slit experiment has not been properly reproduced, but at this point, I don't believe that.
more, and I'll explain that a little later. Just to recap, in the trailer video T8, I demonstrated that the particle wave duality was nonsense. Physicists were treating the corpuscular nature of their detection device as the corpuscularity of light. In other words, they're attributing the corpuscular nature of their luminous detector, what they call a photon detector, as the corpuscularity of light. They cannot do that. And we have a demonstration at the end of this video for the
Yeah, on that part
photon
is kind of is not really right, but okay.
No, but it's about many things that I don't agree with him.
It's not
He's
about
not-
not agreeing with him. It's like photon. The idea of photons was because of the quantization because of the UV catastrophe and Planck. It wasn't about that, but indeed, like when people say that, because on YouTube you see a lot of people saying that the detector detects photons, but of course the detector doesn't detect photons or electrons. If someone's saying that, that's just completely wrong. That's I
I
mean, he's
don't
saying
know.
that, but I don't think physicists really believe that. That's the thing.
I don't know. I honestly don't know.
No, the detector doesn't detect photons. Like
I don't know.
really
So
what happens.
I have to assume that people that are dedicating their lives to these experiments, I'm assuming that
Never assume that. You never assume that.
I have no alternative.
No, you should never assume that. The alternative is not assuming that. So you have one.
No, I mean, I can easily discount all experiments that I did not conduct, but there's no
Yeah,
point
I
in
mean,
that.
but that's not what I'm saying either. Like, I think he's thinking that physicists generally agree with what you see on YouTube, which is like when you look into the double slit experiment animation on YouTube or something like that, they say that it detects photons in the plate. No, that's not possible. But I don't think physicists.
Why is it? How do you
That's-
know it's not possible? What's your
No, that's not
evidence?
possible. I mean, he
How
explains
do you
that
know?
in the second paragraph. You can read it.
Okay, all right.
And-
In this paragraph,
yeah,
also the structure
that's
of
just how
light
the
is
detector works. It's got nothing to
you're
do. It's how with photographic
saying
film works. It's
you're
not just
saying
photons.
okay. So you're saying let's read it. If the structure of light is small enough to enable us to image the structure of matter, then no instrument made of matter can have small enough structure prove the existence of photons. This is essentially Nyquist sampling theorem.
Yeah.
I don't know what he's saying here.
If the structure of light is small enough to enable us to image the structure of matter, that means that the structure of light is smaller than the structure of matter.
What do you mean
Then no
small?
instrument made of
What do you
matter
mean
can
structure?
be.
I don't know what you mean. I don't know what you mean by these things. I don't know what is structure of matter. I don't know
Matter.
what you mean.
Just
Yeah, I
anything.
don't know
If
what
you
do you
can,
mean?
if you're using
I don't
light to
know.
detect matter, and the light can detect all matter,
I don't know what that means.
you don't know
So
what that
we
means.
know. I don't know what you mean. I don't know what you mean. I can repeat this multiple times. I don't know what you mean. What do you
I
want me
don't know
to
how to
do?
explain better. It's like this. For example, you have
No,
like a very
no.
like
Let me ask.
you have like
No, let me
a
ask.
pen,
Let
and you
me
can
ask the
write on
question.
paper with a pen, right?
No, let me ask a question. Look.
Okay.
Okay, look, it doesn't matter. Let's. I really, I just want to
Yeah,
get
it
into
doesn't matter.
Bell's theorem. I just want to get into Bell's theorems. So let's forget about this. Let's just keep going because otherwise we're
Yeah,
gonna
you
have
can skip to the
many.
next section even. So if you want.
You don't want to just go watch a Bell's theorem video.
No,
Why are we watching this guy?
he will explain it. There's no problem.
He will explain
Yeah. Okay.
where here.
Go from there.
We call it the photon detector. Explanation of it. It would demonstrate that polarizers were not spooky, the simple engineering technique.
Yeah.
I'm using a wave. And just like a water droplet hitting the surface of a pond, like you see in the picture, when you disturb it, you end up creating a wave ring that moves out from the point of disturbance equally in all directions. Okay, so considering these directions here, you have a wave front that's moving off in this direction and another wave front that's moving off in this direction. They're going to have both have the same polarity.
I don't know what you mean by polarity.
Okay,
What
and
do you
the
mean
amazing thing
polarity?
about this, if you consider the phasing of their real and imaginary components using Euler's equation.
What polarity? There's no. I don't know
I
what.
mean,
No, look. Light is three-dimensional, so light has polarity because an electron can move up and
I
down,
don't know what
or
that
right
is.
and left. I don't know if there's. What do you mean by? I
No,
don't
but
know.
that polarity is a characteristic of a wave. It's the
What?
orientation or the direction of the oscillations in a wave relative to reference
There's no
direction.
two waves. There's no two ways for these waves. There's no polarity in surface water waves. Polarity is light can be polarized because
No,
an
there is polarity in mechanical waves.
yes. What do you, I mean? Sure, but not in surface water waves. You don't have. You cannot. There's no polarity
So
here.
it's the direction of displacement
There's
relative to
no.
the reference point.
But there's only up and down.
Yeah,
With an electron, you can have up and down, left and right, forwards, backwards. You can have, or you can have any other direction. You can have 360 degrees sphere directions. There's an infinite number of directions that a
yeah,
light
but
light can.
polarity in this case is just up.
Okay, so that's so I don't. So I don't understand. I don't understand what he's talking about. I mean, there's no polarity. The issue of polarity doesn't exist here. I don't know what he's talking about.
This guy, they have opposite spins.
What? What spin? What spin are you talking about? Where's the
Yeah,
spin?
you don't understand, like, you're not understanding how mechanical waves work.
What spin? How do you?
I will look for an animation of this.
No. Look, I just want to go watch Bell's theorem video.
No, this is important. Let me.
I don't understand. I don't understand anything he's saying.
Because they're
Yeah, but
propagating
I will try to explain to you what he's saying. Wait a
So
minute.
why are we trying to understand his video? Why not just go watch Bell's theorem and try to understand ourselves
This
Bell's
video has
theorem?
everything. Why not watch this video?
Because I don't understand it.
Yes, I'm trying to
It's nonsense.
explain.
Look, there's too
Let me
much
give you an
nonsense.
animation that
Too
explains.
much.
Wait.
So you,
Gotta be a
Why
little bit
you-
more patient.
why do you insist on listening to this video right now? We can come back to it later.
Okay,
opposite
fine.
directions.
What?
Okay, fine. If you want.
Yeah,
Yes, fine.
honestly, I don't understand anything he's saying thus far. Thus far, look, I don't like this guy. This
You don't
guy,
want it.
I don't like him. There's nothing about him that I like. I've listened to his videos. I don't like his videos. You know me. I'm very mainstream when it comes to everything. I completely
When it
agree
comes
with
to everything.
what?
When it comes to everything.
I agree with the mainstream on everything. What do I disagree with them on? I don't have any
Physics.
disagreement.
The
No.
ether.
No,
The view
Einstein
on submissiveness.
of what?
Submissiveness.
Submissiveness? I don't.
Yes.
There's nothing to do with that. Anyway, so I don't disagree with the mainstream. Like I don't disagree. Like special relativity, I agree. I just have a different perspective. General relativity, I agree with a different perspective. Quantum mechanics, I agree with a different perspective. I agree with everything they say. I don't disagree with Heisenberg's uncertainty. I don't disagree with Schrodinger's equation. I don't disagree with any of the results that they
You don't
got.
disagree? Okay.
No, I don't. Of course I don't. I just have a different perspective.
Trying to look for this.
And this guy Distinti, he disagrees with things that I agree with. So, and I listened to this video.
That's just life.
What?
That's just life.
What do you mean that's just life?
Yeah, no, people will disagree with things that you agree with.
Look, I can't watch a video of a guy that I don't understand. Everything he said thus far, I don't
Okay, just watch
understand.
another video. That's fine. I already said.
So let's go watch.
I'm just looking for how to explain to you polarization and.
I understand polarization. He's just not.
The other one. What was the other one? The spin. Yeah, the spin of a wave.
I understand spin. There's no spin in
the spin of a wave. Trust me.
The spin of a wave. Yeah.
I'm trying to look.
Okay, Bell's.
If I can find an animation of this, but it's not easy.
Okay, Bell's theorem. Minute physics. Let's give the Venn diagram paradox. The Venn diagram? What?
The Venn diagram. What the hell is that? Like, let that be. The Venn diagram paradox. These people are crazy.
Well, I don't know.
If you have polarized sunglasses, you have a quantum measurement device.
Each of these pieces of glass is what's called a polarizing filter.
Okay, that's bullshit. Get that video out of here.
Why?
That's BS. That's like the.
Why is it BS?
No, that's not how polarization works.
Why not? They didn't even explain yet.
That's BS already.
What's BS?
I've already heard BS, and it's like 1 second.
What? What's the BS? What's the BS?
Yeah, that's saying that polarizers are quantum devices. Okay. Sure.
Okay, let's listen to them.
God, there's like no animations of this.
When a photon of light reaches the glass, it either passes through or it doesn't. And whether or not it
Yeah, this makes perfect sense.
No.
Right? Look, either the
I found it on Bing. Bing is my saving grace.
a photon has a direction. It's polarized.
Yeah.
So photon. So
Google sucks. Will remind me to go to Bing.
the filter. So the filter. I mean, depends which filter.
Means when a
So-
photon of light reaches the
Okay, watch. Look at the
No,
GIF.
no. Why? What do you want to do?
No, just takes 2 seconds. This is spin of a transverse wave.
Okay. So that's
Yeah,
not
that's what he's talking about.
okay. I could have told you this. I mean, I happen to have
No,
done.
it's not difficult. It's just that to explain this with words is kind of difficult.
No, but that's not spin of an electron.
You will explain that in the video, but we can watch the video. You can come back to the video later.
There's no surface water waves in the lifetime of an electron. An electron lives in 3D. Water surface waves are 2D.
No, they can be
the-
3D as well.
Water surface waves?
Yeah.
I don't think you can have, I don't know. I don't think that's the spin because that's the waving. The electron seems to have spin, like magnetic spin. So I don't know how it does that. So I'm gonna let that go for now. Let's go back to this guy.
glass, it either passes through or
What I don't understand is they didn't explain. It looks like they're halfway through some other video. Is this the second part? Watch the second video. And this is the first one.
No,
So
it's
I don't
the
know.
first
Photon passes through. Photon is blocked. Why is the bottom one blocked?
it doesn't. Whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets of polarized sunglasses or old photographic filters. Look through one set of sunglasses at some light source, like a lamp, then hold a second polarizing filter between you and the light. As you rotate that second filter, the lamp will look lighter and darker. It should look darkest when the second filter is oriented 90 degrees off from the first. What you're observing is that the photons with polarization that allows them to pass through a filter along one axis have a much lower probability of passing through a second filter along a
Okay, so there's two filters. One is up down, and the second one is right left. So the up down, let's say it lets this photon through, but it cannot let this photon through. So photons that make it here, make it here.
No, 0%.
That doesn't make any sense.
that allows them to
No,
pass
it's 0%.
have a much lower probability of passing through a second filter
Oh, equals the probability equals 0%. Okay.
along a perpendicular axis. In principle, zero probability.
But here's where things get quantumly bizarre. All these filters do is remove light. They filter it out. But if you take a third filter
Yeah, he's about to say something that is absolutely incredible. I don't know how this works.
and orient it 45 degrees off from that first one, and then you put it in between the two, the lamp actually looks brighter. This is not
Yeah, I don't know how that happens.
the middle filter generating more light. Somehow, introducing another filter actually lets more light through. With
How is that possible?
perfect filters, if you keep adding more and more in between at in-between angles, light through. With perfect filters, if you keep adding more and more in between at in-between
I think
angles,
this Tinti had a video on this, yeah.
What?
This Tinti had a video explaining this.
Okay.
it actually continues. More light.
This feels super weird, but it's not just weird that more light comes through. When you dig in quantitatively to exactly how much more light comes through, the numbers don't just seem too high, they seem impossibly high. And when we tug at this thread, it leads to an experiment a little more sophisticated than this sunglasses demo that forces us to question some very basic assumptions we have about the way the universe works. Like that the results of experiments describe properties of the thing you're experimenting on, and that cause and effect don't travel faster than the speed of light. These will come into question.
Where we're headed is Bell's theorem, one of the most thought-provoking discoveries in modern physics. And to appreciate it, I really do think it's worth understanding a little of the math that we use to represent quantum states, like the polarization of a photon. And we actually made a second video showing more of the details for how this works, which you can find on 3 Blue 1 Brown. But right now, let's just go ahead and hit the main points. First, photons are waves in a thing called the electromagnetic field. And polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening. But unlike a water wave or a sound wave, photons are quantum objects, and as such, they either pass through the polarizer completely or not at all. And this is apparently probabilistic, like how we don't know whether or not Schrodinger's cat will be alive or dead until we look into the box.
For anyone uncomfortable with the non-determinism of quantum mechanics, it's tempting to imagine that a probabilistic event like this might have some deeper cause that we just don't know yet. That there's some hidden variable describing the photon's state that would tell us with certainty whether it...
They're going into the explanation instead of presenting the problem. The question is, what's our solution to this Venn diagram?
Yeah, but if you think about it, it's not that weird. It's counterintuitive.
So what's your explanation?
Well, I mean, like when you make them, when you do them like you put them like 45 degrees from each other, there's some light that passes.
Okay, but you put them 90 degrees at each other, so
No
light.
Because the polarizers will change the polarization. So
What?
Yeah, the polarizers effectively change the polarization of the light.
I don't understand.
The polarizers effectively change the polarization of the light. So yeah.
It doesn't change, it filters. What do you mean it changes?
It filters, but it's like if it's like vertical and you put the 45 degrees, then you will get mostly light polarized at 45 degrees.
1 second. You have a first filter that filters through only vertical light. Then you have another filter that filters
No, it
through
doesn't
only...
filter through only vertical light. That's the problem.
What do you mean? That's what
More like it
polar
filters
light...
out horizontal light.
1 second. All right, let's look at the experiment again. Okay, here's the experiment.
Weird, but it's not just...
Okay, so this one filters exactly this direction, okay?
No, it filters out the opposite directions. You have to think about the filter as something that keeps things out.
It just... Okay, what is a filter? It's just lines. It's made out of lines, like a comb. It's made out of columns that are all in this direction. Tiny, tiny lines. Many.
So it filters out the opposite direction. Right, okay.
So it filters through. What comes through is only light that is in this direction. Okay? What comes through is only one direction of light.
No. That's the opposite.
There's lines. It's made out of lines. It's a comb.
Okay, so light that is in that direction will indeed go through, and light that's vertical.
Only light that is waving this way can come through.
No, if it is a light at an angle, it can go through, but it won't go through entirely.
No. But I don't understand.
It makes sense because the light that's going through the other one is at 45 degrees.
Look, this direction comes through. Only one direction comes through, right? Only this direction. Only one direction comes through.
Yeah.
Right? Okay. So only this direction.
But you're thinking about only one direction comes through. But if the light is going at 45 degrees from that direction that comes through, then the light will be polarized to the direction that it comes through.
Only light of this direction can come through, and that's
No,
why.
it's like
why
you're
is
not
this?
making the distinction properly.
So why is this
Not
black?
making the distinction properly.
The way I understand it, only this direction comes through.
Yes, the
So
light
when it,
after
so
that will be in that
so
direction. And if you only give
what
light
do you
that
mean
is
after?
perpendicular to
What
that
do you,
direction, then no light will come through.
I don't understand.
Okay. Like you should watch. I think Distinti. I remember watching this video some years ago of Distinti, and I think he explained it very well.
Explain
I'll
what? I don't. What is there
explain
to
what I'm
explain?
trying to explain to you. That the light will indeed then become polarized in that direction, but it will be in that direction. But you can, yeah, the intensity, if you the intensity in the perpendicular direction is 0, but the intensity in 45-degree direction to that is not 0. It works, and there's some light that goes through. So it's nothing surprising about this.
I wanna love you.
Hello,
Cause
Andrew.
biggest feeling about from you, Jesus, is my Savior. And Jesus is the
Andrew,
Andrew,
I
showing his
went
singing skills.
through.
Andrew,
I
what's up?
went through just. Oh wait, yo. You're live streaming?
Yes, we're in the middle of a discussion.
Oh yeah, my bad for corrupting it.
Want to join the live stream?
Andrew, do you have something you want to talk about?
Oh yeah, I was watching your live stream on YouTube, so I just said, I can join.
Yeah, you can
I
join,
like
but
seeing you
do you
live
have
streaming.
do you have a question? Do you understand what we're talking about?
Oh yeah, I think you're super coherent.
Okay.
I believe.
Anyway, okay. So the way I understand filters is as follows. So you have one filter that is in this direction. That means it's made out of lines that are in this direction. Many lines like this. So only waves that are waving this way can make it through. So far, do you agree or
No.
disagree? No? What do you mean?
You keep making the same mistake. The
What do you mean?
waves will be polarized in that direction. And if you only get waves that are already previously polarized perpendicular to that direction, then no light will come through.
Okay, I don't know what you just said. I'll repeat what I said, and you stop me when I say something wrong. I'll
That's
speak
what I'm
slowly.
doing.
But stop me as soon as I say something you disagree with. Okay, so this is
Okay.
polarizing.
No, wait a minute. First of all, light goes in all directions.
No, before the light, let's talk about this polarizing lens. What is it really? It's made out of tiny lines, parallel lines, like a comb. So there's space. Where there is white, it's space, and the red is the comb. So the red blocks the light, and the white lets the light through.
Yeah,
Okay.
sort of like that.
Okay. Next is, what do you mean, sort of?
I mean, those things, I don't exactly know what they're made of, but they do have some.
What do you mean?
They have some electromagnetic properties.
No, that's not a polarizing lens. A polarizing lens is just tiny lines. That's all it is. You want to watch a video?
Yeah, it's probably just that.
Okay, so that's all it is. What do you mean probably? I mean, you need to know what it is before we can have a discussion. So, do you want to watch a video what a polarizing lens
No, just ask
is?
ChatGPT what they're made of. I know that's the
Okay, what do you want to do?
wave grid polarized metallic nanowires. Why?
Yeah, metallic nanowires, exactly. That's exactly what a polarized lens is.
Yeah, it's just that. Okay.
Just that. Okay. So only waves that are waving this way can come through, right?
No,
No?
that's the part that's
Okay.
wrong. Like, imagine you send light that goes into all directions.
Wait, how do you know? How do you
No,
know?
I'm telling you. I'm telling you. Imagine that you send light that comes in all directions.
No, wait, but how do you know this? What's your truth foundation? What's your
Yeah, I'm trying to explain, but you have to
No,
do a scenario.
before you what do you mean you're trying to explain? I mean,
What's my
you've
truth
already
foundation? What fits observation 100%, and it has to work like that. Like mechanically, it has to work like that. There's no other way.
Okay, let me ask you. So you've watched this video.
Okay, I think I've watched
You
that video a long time ago. Yes.
No, we just watched it. We just watched it. So there's
Okay.
Do you agree? Do you agree that this is reality, that they're showing us a real effect?
Okay, I'm not questioning that at all.
Okay. So assuming this is the direction of the first slits, right? A polarizing lens is just, it's full of many slits, nanowires. So this is the direction. So only waves this way. Can you see my mouse? Yeah. Only waving this way can come through, right?
No, like I
No?
told you no like 50 times already. No,
Wait.
that's not how it works.
Wait, so you disagree with this analysis?
No, look, if you have a wave that comes at 45 degrees from that,
What do you
some
mean
light will pass
45?
through. But it will be polarized in the other direction. Like
So how do you explain this blackness? How do you understand this
because they're
blackness?
90 degrees from each other.
So what? How do you explain this?
So,
Explain to
so
me.
the light gets polarized on one in a way that's
What do you mean gets
completely different to
polarized?
the
I don't
other.
know what that means. I don't know what that means. Gets polarized. It's a filter. Nothing gets
Hey,
polarized.
you
It's
know
a
what
filter.
polarized light looks like?
What do you mean polarized? Polarized light is the light that has gone through a polarizing filter.
No, that's
What,
not
so,
that.
so
There are
what
other
it,
ways to polarize light. You should
okay,
look
how do
into what
you,
polarization of waves is.
d-
Yeah, look
okay,
into polarization of waves
I
first.
don't just answer. What do you mean look into? Don't tell me what to do. Just have a discussion.
Yes, you have to understand what polarization of light.
Don't talk about me. Just have a discussion. Talk about the topic. What do you want to say?
Okay,
What?
I'm telling you that we should understand what polarization of light is first.
I don't have an issue. I feel like I understand it.
I don't know if you understand it. Then explain it.
I mean, okay. So you have light coming in every direction, but only light going in this direction can come through. Then this second
No,
filter.
like you
Wait,
keep making the same mistake.
but I.
Insisting on that mistake. It's just like every time you say the
What do
same
you
thing,
mean?
and I say
What do
no,
you mean
that's not
mistake?
it.
What do you mean mistake? What do you
No,
mean
that's
mistake?
not it. No, the light that comes from the opposite direction will
Hold
not
on,
come
hold
through,
on,
but
hold
there will
on.
be
You
some
agree?
light in
Hold
that
on,
direction that
hold
will come
on,
through.
hold
Otherwise,
on,
you
hold
couldn't
on,
even have
hold
like.
on,
Otherwise,
hold on,
all
hold.
polarizers would
Wait,
just like be
wait,
black.
wait. Do you agree that they agree with me?
No, they don't agree with you at
They don't
all.
agree? Okay. All right. Let's
Yes, it's
listen
not
from the beginning.
possible. Let me
Okay. Let's listen from the beginning. Let's
If you have
like
polarized
everything
sunglasses,
could be
you
hold on.
have a
black.
Wait, hold on.
Imagine
Let's listen. Let's listen to them. Hold on.
quantum measurement device.
Each of these pieces of glass is what's called a polarizing filter, which means when a photon of light reaches.
Okay.
not enough
So
light.
this has up and down,
When
and
the
the blue
photon-
here.
Let them explain. Like you didn't even let them explain.
Okay.
The glass, it either passes through or it doesn't. And whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets
So
of polarized sunglasses.
okay, that's a very small explanation and not clear.
No. Let's
But you
continue.
understood what
No,
it's
let's
a
continue.
measurement of if it effectively is polarized.
Hold Let's listen.
or
let's
old
listen.
photographic filters. Look through one set of sunglasses at some light source, like a lamp, then hold a second polarizing filter between you and the light. As you rotate that second filter, the lamp will look lighter and darker. It should look darkest when
Okay.
the second filter is oriented 90 degrees off from the first. What you're observing is that the photons with polarization that allows them to pass through a filter along one axis have a
Okay. So as you noticed in this,
What you're observing is that the photons with polarization that allow
right? So the blue, I'm assuming the blue is their direction of polarization. So it's going up and down, and it went through, right?
Okay, so what?
So that's what I kept saying. Only the light that goes up and down. No? Here, let's
them to pass through a
continue.
filter along one axis
Hold
have
on. However, this light is the polarizing is this way, and it blocked the light that
Yes,
went
when
up
they
and
are
down.
when they are 90 degrees from each other, that
No,
happens.
no,
When they are
no,
45
no,
degrees from
no,
each other,
no,
it
no,
doesn't happen.
no. The light came in going up and
What you're
down.
observing is that the photons with polarization that allows them
Okay, that's just an
to pass through a
animation.
filter
Hold on,
along
hold
one
on.
axis
Okay, so the light is coming through the first one. It's going up and down, up and down. This guy, the combs are left and right, so the light does not go through.
Okay.
Do you agree with them, or do you disagree with
That's
them?
not the part where we disagree with.
Wait.
That's
All
the
I'm
part
saying
where
is
we
that
agree with each other. I think is in
hold
your
on, hold
model,
on,
if you were 45
hold on,
degrees,
hold,
the light would not pass.
hold. So I agree with them. Do you agree with them? Yes or no?
I mean, of course, that's not the point.
So what's the point? So why are we having a
Saying
discussion?
that only the light that comes into the light has to already be polarized before coming into the polarizer.
Okay. Let me look up
That's
hold on, polarized light. Let's look up
Okay.
polarized light.
That's what I was suggesting. Now, like just go with waves. None. That's no.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer.
Okay,
It's
that's
designed
we're
to let
gonna
waves-
engage in circular reasoning. Just go to another video.
No, it's good.
You could see that.
But it's either you agree with him.
Just 1 minute and 40. Let's see.
Look, it's either you agree with him or you disagree with him. I need to know who you agree with. That's all I need to know.
Let's watch
waves
the
get
video.
through.
Because I just follow what they explain. I don't know how it works. I follow what they're saying. I'm trying to follow their logic. If you disagree with them, that's a different issue.
In only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through.
Yeah.
You agree with
But we
him?
don't disagree on the 90 degrees. What the
Okay.
hell?
No matter what crazy wave I send,
Yeah,
the left and right-
see. You can send the wave with whatever polarization you want, circular, non-circular. It will pass in that direction. But you can send it in whatever you want. Okay, fine. That video ended up
components get through. It's been
like you already
polarized.
demonstrated what I'm trying to
Now, that
explain
only-
to you.
Hold on.
It works on transverse waves.
You can
it
send the
works on-
wave polarized in whatever way you want.
Hold on. Let me listen.
Light.
No,
Then light is
just
a
understand the previous.
Hold on. Let me listen. Hold on.
Transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for
Hold on.
example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
Okay.
The light. polarizer, but this polarizer is side to side.
Okay, but did
Let's
you see
try
the
it.
part where he sends the light in whatever polarization?
Hold on. Let's
Go
try.
back-
Let's try.
go back to
Wait.
the-
Hold on. Let's try this guy.
No,
I'm
that
pretty
video
sure
ended
that
up being perfect.
What?
The previous video was perfect. Like,
What do you mean it's perfect?
just watch that one, okay.
already heard that light can be polarized. But what does it mean? What is polarized light? Light is an electromagnetic wave. Imagine that this wave is the oscillation of an electron. You are seeing the wave drawn on the board. Do I see oscillation in the coming towards you? Here, the wave of the board is oscillating in the plane of the board and is said to be segment is actually the amplitude. If with the sine curve, you can associate with it. You can just draw a line with the source of light. Let's imagine a lamp. You're receiving not one ray, but many rays. This corresponds to wave vertically. In that case, we say that the light is unpolarized with a cross, and then each tip of the cross there is an arrow, so components of the oscillations. In order to transform unpolarized light into polarized light, we need to make it pass through a polarizer. A polarizer is a device which has an axis of polarization. Components of the light which are parallel to the axis of polarization are allowed to pass. So what comes out of the polarizer are components of the light. Here I choose it vertical. Only the components of the light which are parallel to the axis of polarization are allowed to pass.
Did you agree with this statement?
Wait, I was distracted.
Here, listen again. I'll show you the CC. Maybe it has CC.
Which are parallel.
Listen to what he says.
Only the components of the light which are parallel to the axis of polarization are allowed to pass.
Only
Do you
the
agree or
components of the light, that is, if the light is 45 degrees from that, then it will be half of the amplitude. But this is a bad way of explaining it. The previous video,
Either you agree with him. I need to know if you agree or disagree with him. I need to know. Do you agree or disagree with him?
it's a terrible way of expressing it. But
Just tell me if you agree or disagree with him.
yes, I said I agree, but it's a terrible way of explaining it.
Look, I don't know. If you agree with him, then you agree with me. Then we don't have a disagreement. So I don't know what you keep.
I don't look. You keep making the same mistake, which is that the light that has to come in that the previous light can be polarized.
Let me ask you. Why do you think the way he's explaining is terrible?
The components of the light. What components? I mean.
What do you mean? He showed that light comes out of the filament in every direction.
As long as it's not like 90 degrees, something will pass. Is that difficult to understand?
I don't know what you're saying.
As long as it's not 90 degrees.
No.
And as long as it's not perpendicular.
That's not what he said. That's not what you're disagreeing with him. Then you're disagreeing with him.
No,
yes.
If I'm disagreeing with him, then he's wrong because we've just seen the
demonstration. Okay. That's fine. That's fine. I agree with him, and you disagree with him. That's fine.
Okay, fine.
So that's what I kept asking. If you disagree with, I agree with them. You disagree.
No, you don't agree with the previous guy. Definitely.
I do. With who?
Definitely.
With who?
You do not agree with the previous guy. The previous guy was
this guy.
Now, you might.
Yeah.
I don't agree with this guy.
Now.
Okay. Do the
with
part.
This guy.
Go forward a little bit. Go forward.
No, I didn't. You see that I didn't stop with this guy because he wasn't. I wasn't. It wasn't clear.
It was as clear as possible. Go forward.
No, it's not clear.
Yes,
I don't care what he. I don't care what he said because he wasn't clear. This guy was.
I'm pretty sure.
This guy is clear. So if you disagree,
it's not like if you He's doing like the opposite.
If
He's
you
saying that-
disagree with this guy, it's fine. I agree with him. Then now we know.
disagreeing, like the way he's explaining is just weird.
No, you disagree with him. No,
It's
you
ambiguous.
disagreed.
Like, I
You
can't
disagreed.
because it's ambiguous.
It's
not being
ambiguous.
unambiguous.
Okay, look, it doesn't really matter. I don't know what to do. I don't know what to tell you,
I mean,
honestly.
go to the
Just go ahead
previous
and hit the
guy,
main
and
point.
we will and you will understand it. And I will tell you
What?
when to stop the video and where you
No,
should.
no. Look. It's not important. It's not. I understand what they're saying. I have my idea how light is polarized. You can think whatever you want. I don't know what to do with that. I don't know how light is polarized. I don't have any alternative explanation. The explanation that I gave is satisfactory to me. If it's not satisfactory to you at this
all
point,
transverse waves are polarized in a way.
what?
All transverse waves are polarized. They have to have.
I don't know what that means. I don't know what that means.
You know what a
Don't-
transverse wave is, right?
Okay, assuming it goes, yeah, okay, yeah, I
So it
do.
has to go up. It has to go down. It could be
Yes.
circular. It could
Yes.
go in.
Yes. So
So that's polarization. That's just that. It's not
no, polarization is light that all of it goes in a certain way. Then it's polarized. Otherwise, it's unpolarized.
Yes, that's true.
Okay, so this is what we're watching is a polarized photon or two polarized photons.
Okay, but doesn't tell us much.
Okay.
Polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening.
Yes, the wave.
But unlike a
coming out on
water
the other
wave or a
side.
sound,
See,
Okay,
the wave coming out
yes.
on the other side. See this one,
Yes.
which is like slightly turned. Something still goes through because that part is not absorbed. Right? So you understand. So the wave coming out on the other side is the one that's polarized. The previous wave can be in any direction you want.
I see. Okay.
So that's what I'm trying to
you're
explain.
saying-
Okay, fine. Now we agree.
Yes. So you're saying okay. So it's only so polarizing means it only allows a certain
Yes,
certain
it will
part
allow
of it.
certain component.
That component that matches the filter. Okay.
Yeah.
Okay.
So so then you can like go to the picture that we.
Hold on. I just want to watch the video. Let's watch the video. Okay. Now we finally understand. I understand what you're saying. Okay.
worth understanding a little of the math that we use to represent quantum states, like the polarization of a photon. And we actually made a second video showing more of the details for how this works, which you can find on 3 Blue 1 Brown. But right now, let's just go ahead and hit the main points. First, photons are waves in a thing called the electromagnetic field. And polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the
Is it just for me or is it for you as well? For everyone?
What?
I don't know. The stream is breaking for me, but maybe it's just me.
I'm watching it on my iPhone. There's no issue.
Okay, good.
wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening. But unlike
Make sure I understand what he's saying.
purely in the direction perpendicular so that the wave the electromagnetic field. And polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening. But unlike a water wave or a sound wave, photons are quantum objects, and as such, they either pass through the polarizer completely or not at all. And this is apparently probabilistic, like how we don't know whether or not Schrodinger's cat will be alive or dead until we look into the box.
For anyone uncomfortable with the non-determinism of quantum mechanics, it's tempting to imagine
So what he's saying is it doesn't take a component of a photon. It either lets the photon through or not, probabilistically based on the angle.
That's
Okay.
what he's saying. Yes.
Okay. And they find it difficult to believe? Okay.
It's weird.
But there's no violation of. Look, the only violation is that there is a minimum energy to a photon. You cannot split that energy in two. So if you don't like that, I cannot help you. This universe is quantized. There's no violation of classical mechanics, unless you consider that a violation. But the fact that this universe, right, we know that if the universe was not quantized, then you would have the ultraviolet catastrophe. You would have infinite sunshine, infinite shining in the ultraviolet wavelength.
Yeah, I mean, doesn't seem like doesn't seem very interesting. Yeah.
Right. So, but the question is, why does the third filter bring back light? That I
I
don't
haven't understood that yet. Okay,
What?
because like the light is always going like 45 degrees.
I don't understand.
Right, like what matters is the previous filter. It's never like the three filters don't matter at all.
But that doesn't make any sense. The first filter lets in only.
No, the first filter polarizes light, let's say to 0 degrees.
No, it doesn't. The first one polarizes probabilistically. But by the time we get to the second one, it's completely black.
I mean, depends on the direction of the second one.
Let's say they're 90 degrees to each other.
Okay, that
So
will
now,
of course.
so after the second one, there's no light coming through. How does the third one suddenly let light through?
Oh no, I think you misunderstood then what they were doing. They were putting that one in the middle.
No, they're
Yeah.
not. No, they're not.
Okay, let's see that. Okay, yeah, it's there.
Have a much lower probability of passing through a second filter along a perpendicular axis. In principle, zero probability.
If that's true, then that's the solution. Then it's trivial.
But here's where things get quantumly bizarre. All these filters do is remove light. They filter it out. But if you take a third filter and orient it 45 degrees off from that first,
Oh my God, you're
In the
right.
middle.
Okay, so there's no issue.
No, there's no issue. That's what I'm saying. There's nothing weird about this.
There's nothing weird. It's totally mechanical. These people are insane.
But let's see what he has to say. But now I'm curious
So
about like.
okay. So I mean, he already explained. The first one probabilistically changes it to everything else. The second one probabilistically changes it to everything else. So the third one changes it probabilistically to anything else. So what? I mean, it's just probability. What is the question?
Yeah, I mean, he was saying that the quantities didn't match classical physics. That's what I was more curious about.
He's just worried about the quantities? That's the big issue?
Yeah, I think so. Well, I don't know. I mean, I don't know how this would be different from classical physics because the probabilities will be the same. Like, how will the probabilities be different?
Yeah, why would the probabilities be different than
Okay,
classical?
so I just wanted just kind of curious if they are or not.
Okay.
There's
first
nothing to
one,
do.
and then you put it in between the two, the lamp actually looks brighter. This is not the middle filter generating more light. Somehow, introducing another filter actually lets more light through. With
Yeah, because of the problem, it changes. It changes.
There's nothing strange about this at all.
No, 1 second. Let me think about it.
normal.
The first one, no, we need to think. I need to think about this. Let me think. So the first one modifies it probabilistically. This goes to 100%, and this goes to 0%. So it comes through this guy. So this guy, this direction is 100%. Yeah, it doesn't make any sense. How does
Well,
that work?
well, what are you trying?
Because the first one says that this way there is 0% going left to right. That's what the first one did. So there's 0% moving left to right.
Okay.
So the second one cannot add anything going left to right. Left to right cannot be added by the second one.
No, but the light changes. That's the thing.
What do you
That's the thing
mean?
that the light changes. The polarization of the
That's-
light changes after each one.
That's not, but okay, so that's a different mechanical explanation.
No, that's the explanation that the guy in the short video he demonstrated that how it works mechanically.
But that's not what they explained, right?
No.
They explained that it should be 0% going left and right.
Yeah, the way they
After the-
explain it is different. That's true.
But so according to you, the light changes when it goes through a filter. It doesn't just filter it, it changes it so that nothing is moving left and right, but after the second filter, you would say, yes, now there is something moving left and right.
Yeah.
Okay, that's a different explanation.
Well, let's see
And
what they say about
Between the two, the lamp
probabilities.
actually looks brighter. This is not the middle filter generating more light. Somehow, introducing
so you're saying the middle filter is modifying the direction.
another
Yeah.
filter actually lets more light through. With perfect filters, if you keep adding more and more in between at in-between angles, this trend actually continues. More light.
This feels super weird, but it's not just weird that more light comes through. When you dig in quantitatively to exactly how much more light comes through, the numbers don't just seem too high, they seem impossibly high.
What do you
Yeah, that's
mean?
the part
It's
I
either
want to see. Do they?
it doesn't matter. I mean, nothing should be coming through. Where is this coming? Where? Who cares? What do you mean reasonable and actual? Reasonable is 0. So anything above 0 is weird.
And when we
So the only explanation is that we don't understand how this filter works. And you're right, it actually modifies the light.
tug at
Yeah,
this
that's
thread,
what we
it
demonstrated in that video.
leads to an experiment a little more sophisticated than this sunglasses demo that forces us to question some very basic assumptions we have about the way the universe works. Like that the results of experiments describe properties of the thing you're experimenting on, and that cause and effect don't travel faster than the speed of light. These will come into question.
From this. It's just,
I don't know what he just
what the
said.
hell? I think
assumptions
you're
we have.
exaggerating a little bit.
I can't understand what you're saying. Your audio
No,
is
no,
awful.
no. I was talking like to the video. It's the guy on the video. You know.
No,
That's
your audio is very difficult to understand.
Oh, okay.
Have about the way the universe works. Like that the results of experiments describe properties of the thing you're experimenting on.
The what? The results of an experiment describe the thing that you're experimenting on?
I mean, yeah, if your experiment is minimally good. you
Is
should-
what?
Yeah, I mean, I don't know.
He's like looking with the camera 10 kilometer. This is 10 kilometers red. And he says red 10 kilometers. That's realism. I don't know. What do you mean?
Yeah,
And that cause and effect don't travel faster than the speed of light. These will come into question.
Where we're headed is Bell's theorem, one of the most thought-provoking discoveries in modern physics. And to appreciate it, I really do think it's worth understanding a little of the math that we use to represent quantum states.
I don't like it when they talk about math. They get lost in math.
Like the polarization of a photon. And we actually made a second video showing more of the
I don't like their math, their geometric diagrams. They get lost in that too.
details for how this works, which you can
I get lost in that.
find on 3 Blue 1 Brown. But right now, let's just go ahead and hit the main points. First, photons are waves in a thing called the electromagnetic field. And polarization just means the direction in which that wave is wiggling.
But he's talking about the electric part of the wiggling, right? He's ignoring the magnetic part. Okay.
Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening. But unlike a water wave or a sound wave, photons are quantum objects, and as such, they either pass through the polarizer completely or not at all. And this is apparently probabilistic, like how we don't know whether or not Schrodinger's cat will be alive or dead.
So what is he saying?
Quantum absorption is happening. But unlike a water wave or a sound wave, direction, so that the. But right now, let's just go ahead and hit the
that's
main
weird.
points. First, photons are waves in a thing
No,
called
but
the
it still
electromagnetic.
works the way he's saying. Like,
I'm having a very hard time understanding what you're saying. You
okay,
gotta
but
fix your.
I'm saying that it still works the way it still works with the way I'm saying, even with photons.
What?
It still works the way I'm saying, even with photons like this.
Okay, I don't understand what he's saying. I need to understand. He's saying it in a very weird way. Let me listen.
Magnetic field. And polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening.
That is the weirdest way to say it. Look, he's saying that all the waves come out in a single direction.
Yeah.
But the amplitude depends on the angle.
Yes, exactly.
But it's all in one direction.
Yeah.
But how does he know that? How does he know this? How do they know this?
Well, the tests with the polarizers kind of tell you that.
How do they know this? How do they know this? How do they know this? They don't know this. They're assuming this. I need to know how they know this. The problem with quantum measurements is there is a problem with quantum measurements. So when you make a measurement, you don't know. You don't know what's going on. When you make a quantum measurement, you don't know about reality. The way you measure influences the measurement, influences what you're getting.
But unlike a water wave or a sound wave, photons are quantum objects, and as such, they either pass through the polarizer completely or not at all. And this is.
Wait a minute, so I don't understand. Oh, so it's just a probability, okay.
Is apparently probabilistic, like how we don't know.
So some of them get completely absorbed and some of them make it through, but all of them make it through with the same polarization. Only one polarization can come through.
Yeah.
Whether or not Schrodinger's cat will be alive or dead until we look into the box.
For anyone uncomfortable with the non-determinism of quantum mechanics, it's tempting to imagine that a probabilistic event like this might have some deeper cause that we just don't know yet. That there's some hidden variable describing the photon's state that would tell us with certainty whether it should pass through a given filter or not. And maybe that variable is just too subtle for us to probe without deeper theories and better measuring devices. Or maybe it's somehow fundamentally unknowable, but still there.
I don't know. I mean, they're going so fast when they're throwing so many ideas. I don't know why they do this. Instead of, presenting the data, no, they're going through all the nonsense, the usual nonsense. I don't like the way they're presenting it.
The possibility of such a hidden variable seems beyond the scope of.
What hidden variable? Where are they going? Oh my God. This is a terrible video.
Experiment. I mean, what measurements could possibly probe at a deeper explanation that might or might not exist? And yet, we can do just that.
With sunglasses and polarization of light. Let's go ahead and lay down some numbers here. When light passes through a polarizing filter oriented vertically and then comes to another polarizing filter
Sure.
oriented that same way, experiments show that it's essentially guaranteed to make it through that second filter. But if that second filter was tilted 90 degrees from the first, then each photon has a 0% chance of passing through. And halfway between, at 45 degrees, there's a 50-50 chance.
What's more,
Okay, finally, I mean, this is what they should have said first thing this video began. This is what they should have said.
Of passing through. And halfway between, at 45 degrees, there's a 50-50
That's interesting. So it's 50-50 at 45 degrees, but it's still going to come out only in that direction. Okay.
chance.
what's more, these probabilities seem to only depend on the angle between the two filters in question, and not on anything that happened to the photon before, including potentially having passed through a different filter first.
But the real numerical weirdness here happens for filters oriented less than 45 degrees apart. For example, at 22.5 degrees, any photon which passes through that first filter has an 85% chance of passing through the second filter. To see where all these numbers come from, by the way, check out the second video.
What's strange about that last number is that you might expect it to be more like halfway between 50% and 100%, since 22.5 degrees is halfway between 0 and 45, but 85% is significantly higher. To see concretely...
But the cosine doesn't work like that.
I don't understand what
Why?
you're saying.
No, the sines and cosines don't necessarily work like that, do they?
How strange this is, let's look at a particular arrangement of our three filters. A, oriented vertically, B, oriented 22.5 degrees from vertical, and C, oriented 45 degrees from vertical. We're going to compare just how many photons get blocked when B isn't there with how many get blocked when B is there. When B is not there, half of those passing through A get blocked at C. That is, filter C makes the lamp look half as bright as it would with just filter A. But once you insert B, 85% of those passing through A pass through B, which means 15% are blocked at B. And 15% of those that pass through B are blocked at C. But how on earth does blocking 15% twice add up to the 50% blocked if B is...
Okay, this is too fast for me.
Wait, 15% block.
Why is it
Equals to
15%?
15% block.
Why is the first one 15%?
Once you insert B, 85% of those passing through...
Why is it 85? Did he explain why it's 85%?
I need to make maths with this.
He said that you need to watch a different video to understand the cosine.
pass through a different filter first.
But the real numerical weirdness here...
Okay, wait, so wait, okay, the cosine of 22.5 is 0.87, so that's solved.
happens for filters oriented less than 45 degrees apart. For example, at 22.5 degrees, any photon which passes through that first filter has an 85% chance of passing through the second filter. To see where all these numbers come from, by the way, check out the second video.
Okay.
Okay, so the second video, it's cosine squared.
Oh, it's squared. Why is it squared?
I think it's probability.
Wait.
Or they always
squared. Cosine of what the hell? Cosine squared.
go eat. I'm starving. Are you staying or are you going to sleep?
You can go, but this is what's the difference between the cosine squared like this and the cosine
I think it's that's the way they do probability. It's always squared.
Yeah. Oh yes, it's try to equal 1.
Oh yeah, sine squared plus cosine squared equals 1. Yeah, you have to, so you have to square it. Just to normalize it because of normalization. Okay, let's. I'm gonna stop here. I'm gonna go grab a bite,
Okay.
and I'll call you in a couple of minutes.
Okay, I may
I'll
have
see you
to eat
later.
as well,
Okay, so go eat. Go eat so we can continue.
so I wanna do a few things here. So then you can
Okay,
tell me.
I'll text you when
So
I'm ready.
I'm sorry for the not explaining things very well.
Yeah, it's
Yeah,
okay. It was weird.
yeah.
Next time I'll trust you more. I didn't know why I didn't understand it. Yeah, it was weird.
You're
Okay,
tired.
no, at least, nah, I don't know if I'm tired. I just didn't know. I didn't know what's going on. I mean, I tried understanding you. Look, I'm still confused. It's not like this stuff is not confusing. It's confusing, but so far we understood everything. So I think we'll be able to break
Yeah.
through and write a paper about this. So
Okay.
we'll put quantum mechanics behind us. Quantum mechanics is going to end up being just wave mechanics, like everything else, like
Yeah, pretty
relativity,
much.
probably. Okay, I'll see you
Alright.
later, man.
Yeah.
I'll text you. Bye.